Welcome to the second course in the Introduction to Applied Data Science with Python Specialization. In the first course, we looked primarily at how to manipulate data, including loading data from structured delimited files such as CSVs, cleaning the data with Python pandas and NumPy libraries, and transforming data using functions such as apply, aggregate, map, and pivot. If you don't feel you have a solid understanding of the pandas toolkit, then I would invite you to go back and review that course content. The main topic of this course is understanding how to communicate data more clearly to the various stakeholders who are interested in the data. And there are many different stakeholders to whom you might be interested in using visuals to reach. For instance, you'll want to share unbiased representations of data with peer data scientists who are able to make their own inferences and interpretations. But you also want to be able to share stories about the data with managers and executives who might be familiar with the domain but are looking for specific actionable insights. Finally, you'll also want to be able to communicate like a journalist to a broad population who knows very little about your particular data and needs to understand not only an overview of the phenomena you are describing, but also the limitations of the approaches you have used. This course is about specific techniques which are part of a broad subject of information visualization. Referred to as InfoVis for short, this is a field that has rapidly developed over the past 20 years as computing power has made it possible to build compelling visual and interactive graphics quickly. And while the use of visualizations to impart knowledge of data has been around for centuries, the last 20 years have seen the development of important theoretical bases for best practices in displaying information to various audiences. And in this course, we're going to focus on those. In this first week of the course, we're going to touch on some of those theories and best practices and talk about fundamental thinkers in the field, in particular Alberto Cairo and Edward Tufte. We'll go through some examples of excellent and not so excellent visualizations and develop a language for speaking about how we might make meaningful visualizations ourselves. This portion of the course will be largely lecture-based, with several readings and peer-reviewed assignment at the end of each week. In the second and third week of the course, we'll dive into the de facto Python library for creating charts and graphs, Matplotlib. Now, Matplotlib isn't the only way to create visual artifacts in Python, but it's the basis for some emerging new web tools such as Seaborn and Bokeh, and acts as a solid foundation for our discussions. The majority of these weeks will be spent actually working on assignments with a few lectures to share an overview of how the toolkit itself works. And you'll be expected to take messy raw data, process it using pandas or other suitable techniques, and render it into a meaningful explanatory image. And again, if you're not comfortable yet using pandas, I would encourage you to go back to the first course in this specialization and review those videos. The assignments for weeks 2 and 3 will be largely peer graded. Finally, the course will culminate with a small project, similar to the first course. In this project, you'll be given a new visualization technique, and you'll be asked to extend the Matplotlib codebase to enhance its functionality. This is a critical step in your journey as a data scientist, to go beyond using tools off the shelf and instead be able to modify them to support new ways of understanding data and problems. This course is very similar to the first, except the evaluation is largely peer-reviewed. The lectures will only guide you so much in completing the assignments. You'll need to know how to ask questions in the discussion forums of your peers and seek out new information through web searches and Stack Overflow. And again, Stack Overflow is tagged specifically for questions about Matplotlib, so I'd encourage you to use that resource as well. Finally, for this course, I expect that you are familiar with all of the content from Course 1. I'm looking forward to this next course in the specialization. Let's get started. I'm Chris Brooks. I'm a research assistant professor at the School of Information. I'm director of learning analytics and research at the Office of Academic Innovation. I'm a computer scientist who studies e-learning, student achievement, student success, both in higher ed and in online situations like in MOOCs. One thing I remember as a child, my father was a physicist, and so I would go to the university, as many kids do, and as my kids do now, come and experience the university and what it has to offer. As a physicist, he had access to some of the first instances of the World Wide Web, and so I got to sit there and play with things like NCSA Mosaic, early versions of Netscape, etc. And I think it's that connectivity, the idea that information was now a first-class citizen in the world of sciences. And so this new world that we're starting to see with data science, these are competencies that learners are learning
in preschool that are starting to think about data as a different way of investigating the world. And I think that for me, that started in a very early stage when I was young, at the university, seeing what my father was doing and being able to play with computers. I'm happy to try and bring that to as many people as possible. And that's really one of the goals of this Introduction to Data Science with Python.
In his book, The Functional Art, Alberto Cairo provides a tool for thinking about design trade-offs when building information graphics, and he calls this tool the visualization wheel. In this conceptualization, there are two poles of a circle. The top one represents highly complex data, which informs at a deep level, while the bottom provides easier access to data, but only informs in a shallow manner. Inside the circle are dimensions which describe trade-offs between two approaches. While Cairo provides a number of interesting dimensions, it's important to note that this is a tool for designers to think about their visualizations, and not so much an analytics tool itself. Your needs for any particular problem might change which of these dimensions are important, or might introduce new dimensions which you should be thinking about. Cairo actually suggests our role in an organization or our professional background might also influence the kinds of graphics we want to make. So I'd like to ask you, as someone who is studying data science, who are you trying to reach through your visualizations? Let's dig in and look at a few of the trade-offs that Cairo considers. The first is abstraction and figuration. A highly figurative visual describes the phenomena using physical representations of the phenomena, such as photographs or drawings. As the representations become less real and more conceptual, the emphasis shifts from figuration to abstraction. The second dimension he discusses is functionality and decoration. A completely functional graphic has no embellishments and is closer to a direct representation of the data, while a heavily decorated graphic has more artistic embellishments. As it is with all of these dimensions, there isn't a clear better or worse. Embellishments may increase the amount of time a viewer spends considering the visual, exploring its nuances and forming mental associations, which may increase familiarity and memorability. The third dimension is density and lightness, as they relate to the amount of information being shown. There are lots of great examples of this in scientific visuals, where some figures are intended to be studied in depth, while others are meant to quickly augment a narrative. You can see this dimension at play when comparing magazine infographics, where the reader is likely to be more heavily engaged in the content, to advertisements in the same magazine, where readers are likely to only quickly consider an ad. Here's an example from my field of study, which was published by Harvard and MIT, describing the patterns of access of users in the edX massive open online course platform. Take a moment to study this image. What sense can you make of this image? If we consider Cairo's third dimension, it would be tough not to say that this is a fairly dense graphic. The main portion of the graphic, a scatter plot, has two axes which are labeled, as do each of the two subplots to the left and the bottom, which are histograms. The axes for the histograms can be a bit confusing as they bleed into the scatter plot axes, but change the unit of measure and the direction of the measurement. For instance, in the x-axis at the top of the scatter plot, percentage of chapters accessed is being used as the unit of measure and increases as you move towards the right-hand side of the figure. Yet this same x-axis for the histogram to the left of that graph is in thousands of persons and increases as you move to the left side of the figure. There are some red lines overlaid on the graphic, breaking the scatter plot roughly into quadrants, but with minimal labeling, it's a little unclear what the quadrants end up representing. Regardless of whether this is a good figure or not, it would certainly be considered an example of a dense figure. The fourth aspect Cairo maps is the dimensionality of the graphic. A multidimensional graphic describes a phenomena as a whole and invites the viewer to explore many different aspects of the phenomena. A unidimensional graphic instead focuses on a single or a few items and explores them in one or more ways. The fifth dimension is originality and familiarity. In the modern world, we're used to seeing a plethora of different kinds of information graphics, things like bar charts and line charts. And thinking in terms of these representations is taught at a very young age. For instance, my daughter, who's almost 5, came home from preschool the other day with a page that showed a bar chart that she and others had made in class. To celebrate learning about the American election, the whole class got together and had a vote on what they would have for snack: chocolate ice cream or mint chocolate chip ice cream. Of course, mint chocolate chip ice cream won, as one might expect. But my point here is that these are basic ways of thinking about data in a graphical form, and they're now being taught very early on, and this makes them familiar to a broad population. This wasn't always so, though. It's safe to say that the bar chart is fairly familiar to most people. But a graphic with more originality is elements that need to be explained or studied by the user. Here's a very famous graphic by Charles Mindar. It describes Napoleon's march into Russia in 1812. Take a moment to study the graphic. Broadly speaking, there are 5 different kinds of information being visualized in this graphic. How many of those 5 pieces do you see? Here's what I see. First, there are elements of geography, shown as the various rivers and towns along the way. The width of the tan upper bar represents the size of Napoleon's army, and you can see it shrinks from the beginning of the campaign from 422,000 to only 100,000 once the French reach Moscow. The lower black bar shows Napoleon's retreat from Russia, and there are various points along it which are mapped to dates and temperatures in Celsius. We see the bar thins dramatically as the army shrinks in size. So the 5 kinds of data in Mindar's visualization include location, direction, temperature, army size, and dates. The last dimension which Cairo shares is the novelty and redundancy dimension. Redundancy is the tendency of a graphic to tell the same story in many different ways. For instance, you might use the height of bars in a bar chart with an axis, as well as color, to emphasize the largest bar. This one's a bit tricky. You don't want to bore your readers or make your graphics overly complex, but you do want to encode information in a way which supports their understanding of the phenomena you've described. On this dimension, novelty is the act of describing each phenomenon in the graphic in only one way. There are no rights and wrongs in the visualization wheel. The purpose of the wheel is to help you understand and compare the visual approaches you might take. As a reflective activity, Cairo suggests that you can plot your thinking along each of these dimensions and then join those points together to create a radar plot. Here, Cairo provides 2 examples of the visualization wheel in action. On the left-hand side, you see there's more of an emphasis towards complex visuals, those which are dense, multidimensional, and of high functionality. On the right, you see the visualization wheel. There are more elements of decoration, lightness, and figuration. Cairo suggests that the left wheel is more indicative of work being done by scientists and engineers, while the right wheel is more indicative of work being done by artists, graphic designers, and journalists. This tension between how scientists and engineers might view the visualization of data and how artists and journalists might is an interesting one, and we'll revisit it at the end of next week. In the next lecture, we'll go a bit deeper and consider some heuristics from Edward Tufte as to what makes a good visualization. The visualization wheel is one tool which we have in order to better compare 2 different ways of visualizing information. In the next lecture, we'll dig in a bit and see how you might use the visualization wheel to evaluate your own graphics. Edward Tufte is a seminal figure on how to design visual displays of quantitative information. In fact, this is the title of my favorite book of his, and I highly encourage you to check out his work. In this book, he introduces 2 interesting graphical heuristics: the data-ink ratio and chart junk. First, what's a heuristic? A heuristic is a process or rule that is meant to guide you in decision-making. It is by definition not known to be optimal or perfect, but to be practical in nature. Heuristics are meant to be followed until you have reason to deviate from them. Tufte's first graphical heuristic is data-ink ratio. Tufte defines data ink as the non-erasable core of a graphic, the non-redundant ink arranged in response to variation in the numbers represented. In other words, the data ink is essential to the sense-making process for a given variable. Tufte defines the data ink ratio as the amount of data ink divided by the total ink required to print the graphic. Now, I don't think he's actually suggesting we measure the amount of ink laid down on the page, but instead is suggesting that we remove those elements which don't add new information to the graphic. Perhaps one of the best-known examples showing data ink reduction was done by Dark Horse Analytics, an information visualization and design company in Edmonton, Alberta, Canada. They've put together 4 examples of how the data ink ratio can be improved, and I'm going to link to those in the next reading assignment. But I'm going to walk through the first one of those here. We start with the table of the data about food items and the number of calories in those items. The first step is to remove unwanted background imagery, since it provides no value to understanding the chart. We also remove the gray background behind the bar, since it provides no conceptual value. Then we get rid of the redundancy throughout. This includes getting rid of the legend, since each bar is labeled directly along the x-axis. The title and the y-axis labels are trimmed, since there's plenty of reference throughout the image to this being about calories for food items. This leaves us with a much smaller image. There are some heavy lines forming borders, which add no value, so we can remove them too. Color is a tricky item to include in charts and graphs. We won't be going into depth on color theory in this course, but color is a challenge when trying to engage with persons who might be color vision deficient or colorblind. There are some tactics to work around. For instance, it used to be best practice to replace coloration with patterns, sometimes called hatching, in graphics. This brings its own challenges, which we'll see in a bit. Instead, the solution is almost always to remove all color, except for one which you can use as emphasis, and link to that color in your text. Someone then viewing the chart out of context would still get the sense of emphasis without being overwhelmed by a rainbow of data. So let's drop colors except for bacon, with the presumption that this text is clearly referenced in the data. Three-dimensional bars and drop shadows can go as well, since these don't add extra value. We can also drop the bolding throughout. There's still a lot of grid work left in this image, and it's a bit unclear what the value of this grid work is, so we're going to drop it. Now, grids can be valuable, but they're often just a distraction. For the moment, though, study the image. What's the difference in the number of calories between bacon, our data point of interest, and, say, potato chips or chili dogs? Just removing lines doesn't make it easier to read. But the values of the data are pretty simple here, so let's directly label each bar in the graphic. Now, how big is the difference between bacon and potato chips, or bacon and chili dogs? Certainly you have to do a bit of math, but you can still get a quick estimate by glancing at the graphic and an exact value through comparing numbers directly. And there you have it. By increasing the data-ink ratio, we have made the graphic not only simpler and more readable, but increased the amount of information the viewer sees. I encourage you to check out the other examples from Dark Horse Analytics linked in the next reading, as they've done this cleanup for a variety of different visuals, including maps. We'll continue our exploration of Tufte's heuristics by looking at chart junk in the next lecture. Another heuristic which Edward Tufte introduces us to is called chart junk. Now, Tufte is much more damning of chart junk than he is of other forms of non-data ink. Indeed, he suggests that artistic decorations on statistical graphs are like weeds in our data graphics. He suggests that there's really three kinds of chart junk. The first is unintended optical art, for instance, excessive shading or patterning of chart features, such as shown in this economics graphic, which Tufte shares in his book, The Visual Display of Quantitative Information. Here, the patterns make the human eye jump and cause visual fatigue. These phenomena are called moire patterns, and it's the same reason you don't usually see people wearing striped shirts when filming video content like this MOOC, since the low resolution of the video accentuates the moire issue. Tufte suggests that instead of patterning this content, one is better off labeling the chart graphics directly, and we saw that being used in the data ink ratio example by Dark Horse Analytics. The second form of chart junk is the grid. Tufte suggests that the grid is both unnecessary as data ink, but also causes competition with the actual data being shared. Thinning, removing, or desaturating grid lines makes it easier to see the data, instead of being overwhelmed by the number of lines on the page. Direct labeling of data is another great way to reduce this form of chart junk. But it's the third form of chart junk that I want to focus on here. It's the one which typically comes to mind when talking about chart junk. Tufte calls this the duck. Broadly, he's referring to non-dative creative graphics, whether they be line art or photographs, and their inclusion in the chart. Newspapers and news magazines are a place where this kind of imagery is often used. One well-known graphic artist, Nigel Holmes, has used the duck to display data in a way which is memorable yet aesthetically interesting. One of the most memorable images he's created to me is entitled "Diamonds Were a Girl's Best Friend," and this showed up in a Times magazine in 1982. This graphic shows the trend of the price of diamonds from 1978 to 1982, and while the dollar amounts are easily forgotten, it's easy to remember that the trend had a spike because of the shape of the woman's leg. So is the duck really a useful heuristic, or is it something about ducks which are memorable? I was part of a team led by Scott Bateman who wanted to understand this issue in more detail, so we set up some user testing. I've linked the full academic paper in this week's readings. In short, we provided participants a variety of Holmes's image, including the one which you were shown, which could be considered chart junk. We also included a variety of plain graphs with high data ink ratios, with no decorative embellishments. We brought 24 subjects into the laboratory and assigned them to either view the Holmes or high data ink ratio conditions. We asked the subjects to describe and summarize the charts with a series of guided questions. This was followed with a recall test, both conducted immediately, as well as a second test 2 to 3 weeks later. Finally, we used eye tracking to determine where subjects were paying attention when they looked at these charts. Our findings were interesting. While there was no recall difference when tested immediately, recall after 2 to 3 weeks was significantly better for the Holmes charts, which showed the duck chart junk. Further, subjects indicated subjectively that the Holmes charts were more enjoyable, more attractive, easier to remember, and easier to remember details of, and they felt it was faster to describe and remember the Holmes charts. The non-embellished designs didn't perform better than any of the Holmes designs did. Does this mean that you should use embellishments in your charts? Well, maybe. I don't know of anyone who's replicated our findings on a larger and more diverse population, and there are certainly other kinds of chart junk, like the unintended optical art and the grid, which seem like really good heuristics. But I think there's more to be told in this story and more nuance to be worked out. At this point, you should have at least some thoughts from designers, as well as from a user study, on specific kinds of charts. And as you go about creating your data science graphics, it's worth not only reflecting on the principles you use and the results you are sharing, but also the process by which you came up to create the graphics. Setting up a user study is much simpler today with crowdsourcing services such as Crowdflower and Amazon Mechanical Turk. It's now very reasonable for the average data scientist to test out whether more embellished visuals might be more effective, whether it's in terms of time, memorability, accuracy, than those with data ink. In the next lecture, we're going to go on to touch on 2 more items from Tufte, the lie factor and sparklines. Edward Tufte's emphasis on simplicity and minimalism has grown a great following. He is largely seen as one of the most influential writers on the topic of visualizations for charts and graphs. In his book, Beautiful Evidence, he introduced the idea that took minimalism in charts to a new level. Instead of making a chart a separate artifact to be studied on its own, he suggested that it be reduced and embedded within the context of discussion. He argued that a small graph, say a time series line graph, could convey so much more information quickly that it would be invaluable to readers. He called these items sparklines and referred to them as data words, an intriguing way to bridge the gap between text and figures. He suggested that sparklines could not only be represented directly in text, but also could be embedded in tables along with the data they describe. This thought became so natural that it's even been picked up by one of the most common pieces of spreadsheet analysis software, Microsoft Excel. Here's a picture of tabular data from the NASDAQ Stock Exchange, showing the opening price of 4 technology stocks over a 1-month period. Take a moment to consider this data. Which stock has had a bad month with a downward trend, and which has had a good month with an upward trend? What if I added sparklines in the cells below? Here you can see immediately that Apple has had a poor month with decreased stock price, and IBM has had a good month with increasing stock prices. With Amazon and Intel, it's a little less clear, and we see some spikes throughout. Now, these sparklines don't help us answer who has the highest stock price or who had the greatest wins or losses, but they do give us a general feeling for the trend behind the data. And actually, sparklines are used for data where trends or distribution characteristics are important. Here's another example of sparklines used in Google Finance's website. Notice how you can actually quickly zoom in on pieces of the distribution with these sparklines. So they're not just a representation of the data, but a method of interacting with it. There have been lots of different uses of sparklines, and customized interfaces such as video games are a great example. A modern take on sparklines, which I think of is kind of neat, is called the Spark Tweet, where Unicode block characters are used to display a bar graph inside the 140 characters allotted by Twitter. For instance, here a user has tweeted her hours of sleep over the month of April as a bar graph. The last Tufte principle that I want to share with you is one called lie factor. Lie factor is the size of an effect shown in the graphic divided by the size of the effect actually in the data. It's often done unconsciously to try and help tell a narrative. However, it's misleading to the observers. There are lots of different examples of lie factor. This one from Time magazine in 1979 provides a great example, I think. In it, various barrels of oil are shown, showing the price of oil over 6 years. But it's unclear to the viewer what the size of one barrel means in relation to the others, in part because there's an element of perspective here. Are the barrels different sizes, or do they just appear to be so because some are in front of the others? Is it the volume of the barrel that represents the growth of the cost, or the height of the barrel? Spark lines and lie factor are just two more tools that Edward Tufte has given us to understand and communicate data. I consider Alberto Cairo's book, The Truthful Art, to be required reading for any data scientist. In one book, he's managed to pack in a plethora of references to experts in the field while still distilling down details into memorable lessons. While we won't have an opportunity to cover everything he talks about, I want to talk in this lecture about the foundation of the book in particular, which is a 5-part framework for considering the qualities of an information graphic. Importantly, Cairo says that these qualities are not independent of one another and that they're interrelated. So while I tend to be prone to reductionism, keep in mind that the different qualities interact with one another as we go through the lecture. The first quality of a good visualization is that it's truthful. Now, Cairo admits that truth could be considered subjective and is certainly on a continuum, with some things being more truthful than others, and that it might be impossible to establish an absolute truth. But as data scientists, he argues, we have two obligations when it comes to protecting the truth. First, we have to be honest with ourselves. When we clean and summarize data, are the activities we're engaging in likely to obscure a message because of the limitations that we've applied? We should consider explicitly each modification that we're making to the data and make sure we aren't practicing what he calls self-deception. Skepticism is an important skill for data scientists, and we often get so focused on looking for patterns that we reduce or present data in ways which are inauthentic to the phenomena being described. The second obligation is to our audience. That is, there are techniques in data science and information visualization which we can use to shine light on specific pieces of data. Indeed, this is generally the point of the fields. But if we omit the ability of the reader to explore the phenomena more fully, this will generate doubt and cast distrust. Cairo gives us a great example of this, using a chart inspired by one put out by the lobbying association, the National Cable and Telecommunications Association. This association lobbies on behalf of U.S. cable companies and provided a graphic which suggested that after regulations were relaxed, cable companies invested 4 times as much in the industry. Now, the original chart has been taken down, but Cairo provides an example of what was visualized. And we can see here the title of the chart alone was intended to draw the reader to the conclusion. Less regulation means more industry investment. But there are some immediate problems with this graphic. First, it's unclear whether the monies are adjusted for inflation, which is a big issue when providing charts of financial data. Second, the time spans for the 2 bars are different. One covers a span of 3 years, while the other covers a span of 4 years. Think of this through the lens of Tufte's lie factor analysis. The bars have the same width, but don't represent the same period of time. This is a completely unforgivable design choice. And finally, there seems to be a bunch of missing data from years 1997 and 1998, and the chart stops in the year 2003, but the information was tweeted in 2014. What does a more honest view of the data look like? Well, Cairo tracked this down and provided a line graph. We can see that after regulation, there were, in fact, years of sustained industry investment. We see a slight drop after deregulation, then a massive spike in spending, and then a significant fall from the period post-2002, much of which is excluded from the original chart. While it's unclear whether the dollar values are in fact corrected for inflation, it seems pretty unreasonable to suggest from this data alone that regulation stems cable company investment in infrastructure. The lesson here is that while there is maybe no absolute truth, there are ways of displaying data which are more truthful than others. The second quality of a visualization to consider is whether it is functional or not. This again is a continuum, and we saw an example previously where the slides on data ink ratio provided by Dark Horse Analytics. If you expect your audience will want to compare two data series, direct labeling of them is one way to increase comprehension. While there are many heuristics for increasing functionality, I would like you to remember the user test we did with ChartJunk. I think now is an exciting time for understanding situated human behavior. The web has dramatically increased our ability to test social and behavioral hypotheses at scale across diverse populations, and Crowdflower and Mechanical Turk are just two examples of this. Understanding how functional a given approach to a visualization is doesn't necessarily require expensive ethnographic research. It's now much easier to test hypotheses directly with crowd sources. The third quality of visualization Cairo shares is whether it is beautiful or not. I think that this requires knowing a great deal about your audience. There are different perceptions based on people's lived experiences and aspects about themselves such as gender and culture. There's a lot to building a beautiful information visualization experience, which depends on situational and contextual factors too. For instance, if you're building a chart for a report, the colors and styles that you might choose, even down to the font choice, might be more related to beauty than, for instance, function. But the interplay of these elements is something which is difficult to ignore. I wonder, is this broad topic of beauty one of the conflationary factors of the ChartJunk memorability issue? Whereas Tufte argued that the duck junk is distracting and misleading, the study by Bateman et al. Showed that it can make visualizations more memorable. Is this disconnect an issue of beauty in information graphics? Here's one parting thought on beauty and information that perhaps drives home this quality. One of the most popular tech magazines, well known for its full-page information graphic spreads, is Wired magazine. On Wired's website, they tag these articles as infoporn, a reference to the visceral reaction that they hope readers will feel when viewing the articles. The fourth quality of visualization from Cairo is that information graphics should be insightful. They shouldn't just replicate data in tables, but they should draw the viewer in such that the viewer has an aha or eureka moment. I think about this largely in the context of academic papers, where I do most of my work. A common issue that novice writers have in this area is the inclusion of a figure for every piece of data they have. This is really unnecessary and adds bloat and contributes to reader fatigue. But the right figure drives home the results of a study quickly. Scientific peer review is common in my field, but readers don't have the large amounts of time that they need to do full reviews. When flipping through a submitted paper, if the reviewer sees an image which jumps off the page and gives them immediate insight, this sets them up to understand the more nuanced story to be told throughout the rest of the paper. The final quality of visualization which Cairo proposes is information graphics should be enlightening. This is different than insightful. In fact, Cairo argues that this quality is composed of the previous four: truthful, functional, beautiful, and insightful, but is separate in that it adds a social responsibility dimension. I don't think there's an obvious answer to this question, but without a doubt, Cairo's 5 qualities of great visualizations, being truthful, functional, beautiful, insightful, and enlightening, are well worth considering. Cairo has more great work, and following this lecture, I've assigned a reading of his, as well as a discussion question, to encourage you to weigh in on the amorality of information visualization as it relates to data science. And this ends the week of the course. We've covered a lot of material very quickly, but I really do believe that these two authors, Alberto Cairo and Edward Tufte, are fundamental in building a strong foundation for the applied data science skills we'll focus on in the second week of the course. Welcome to the second module in the course Applied Plotting, Charting, and Data Representation in Python. In the first module, we touched on some of the fundamentals of putting together good information graphics, drawing on influential thinkers in the field such as Alberto Cairo and Edward Tufte. In this module, we're going to pivot and focus on skills for building basic charts using the Python-based Matplotlib toolkit. Matplotlib is a powerful open-source toolkit for representing and visualizing data. Its creator, John Hunter, was heavily inspired by the MATLAB programming environment and borrows many of these elements. Matplotlib can be a bit confusing to learn from web resources. There's a traditional object-oriented API, but there's also a MATLAB-like scripting model, and I've found that it's not always clear why a given script from a blog post might work or not work. I'm going to try and demystify this a bit for you by providing a structured introduction to the toolkit. After the architecture introduction, we're going to dive right into creating charts and graphs. In this module, we're going to focus on some of the basics: scatter plots, line graphs, and bar charts. We're also going to touch on how to label pieces of your charts to improve readability and draw the user's attention to specific details, and how to manipulate data elements in the plotting environment. From here on out, there will be fewer lectures and more emphasis in the module will be put on the plotting and charting assignments. At the end of modules 2, 3, and 4, you should be able to produce publication quality charts and figures using a breadth of data. Let's dive in. We're going to use Matplotlib within the Jupyter notebooks, just like we did with pandas. Jupyter has some specialized support for Matplotlib, and this is enabled by using the IPython magic %matplotlib notebook. Remember that in the Jupyter notebook, the IPython magics are just helper functions which set up the environment so that the web-based rendering can be enabled. Matplotlib itself can work well outside of the Jupyter environment. But for this course, we're going to focus on its use within the web environment, in part because of how popular Jupyter has become in data science practice. So what actually has happened when you run the magic function matplotlib with the inline parameter is that matplotlib has been configured to render into the browser. This configuration is called a backend, and Matplotlib has a number of different backends available. A backend is an abstraction layer which knows how to interact with the operating environment, whether it's an operating system or an environment like the browser, and knows how to render Matplotlib commands. In fact, there's a number of different interactive backends, but there are also backends called hard copy backends, which support rendering to graphics formats like scalable vector graphics, SVGs, or PNGs. So not all backends support all features, especially interactive features, which we'll touch on later in this course. Let's import the Matplotlib library, which we'll do as MPL, and call getBackend to make sure we're using the nbag backend. Great. You'll notice that Matplotlib has a lot of non-Pythonic naming conventions. In particular, you'll be accessing variables using the get and set, which is an accessor pattern which is more common in languages like Java. This is just something you have to get used to, but remember that you can hit tab for type hint autocompletion in the Jupyter notebook, so this can help you find the functions that you're looking for. Now, we're not going to spend much time with the backend layer, but it's important to be aware of. If you're on macOS, for instance, your default backend when using Matplotlib is one system, while on Linux, GTK is my default backend. The next layer is where we'll spend most of our time, though, and that's called the artist layer. The artist layer is an abstraction around drawing and layout primitives. The root of visuals is a set of containers, which includes a figure object with one or more subplots, each with a series of one or more axes. This last object, the axes, is the most common one you'll interact with, changing the range of a given axis or plotting shapes to it. And just a brief aside, especially since this is a global classroom with people from around the world enrolled where English might not be their first language. Matplotlib relies heavily on the axes object, which is the plural form of axis. But Matplotlib also has an axis object as well, and an axis is actually made up of two axis objects, one for the x, horizontal dimension, and one for the y, or vertical dimension. So you might hear me pronouncing these two words, axes and axis, a bit more intentionally than I would in regular speech in order to help make things easier to follow. The artist layer also contains primitives and collections. These are base drawing items, things like a rectangle, ellipse, or a line, and collections of items, such as a path, which might capture many lines together into a polygon shape. Collections are easy to recognize as their name tends to end in the word collection. It's worth taking a moment to look at the kinds of artists which are available. Here's an image from the Matplotlib documentation on artists. You'll see that there's lots of child objects of the artist object, and that one of them is called patches.patch. This name comes from the MATLAB roots of the project, and a patch is any two-dimensional object which has a face color and an edge color. And children of the patch class are the primitives, as we've discussed. Okay, so Matplotlib has two layers. A backend layer, which knows about low-level graphics routines and can render to the screen or to a file. We'll use the inline backend for most of our work. And the artist layer, which describes primitives, collections, and containers. It knows how figures are composed of subfigures and where objects are in a given axis coordinate system. So with this, we can actually get started building figures and rendering them. But there's one more layer which is extremely important for us as data scientists in particular, and this is called the scripting layer. You see, if we were writing an application to use Matplotlib, we might never care about the scripting layer. But this layer helps simplify and speed up our interaction with the environment in order to build plots quickly. It does this, frankly, by doing a bunch of magic for us. And the difference between someone who is effective with Matplotlib and someone who isn't is usually based on their understanding of this magic of the scripting layer. The scripting layer we use in this course is called PyPlot. So that describes the Matplotlib layer cake. There's a backend, which deals with actual drawing, a bunch of artists on top of the backend, which describe how data is arranged, and a scripting layer, which actually creates those artists and choreographs them all together. I just want to address one more topic before we move on, and that's the difference between procedural and declarative visualization libraries and, well, user interfaces more generally. The PyPlot scripting layer is a procedural method for building a visualization, in that we tell the underlying software which drawing actions we want it to take in order to render our data. There are also declarative methods for visualizing data. HTML is a great example of this. Instead of issuing command after command to the backend rendering agent, which is the browser with HTML, HTML documents are formatted as models of relationships in a document, often called the DOM or document object model. These are two fundamentally different ways of creating and representing graphical interfaces. The popular JavaScript library, for instance, d3.js, is an example of a declarative information visualization method, while Matplotlib's PyPlot is an example of a procedural information visualization method. In the next lecture, we're going to get dirty and start making some graphs. But before we do that, I wanted you to check out an article by John Hunter and Michael Drottenbaum. While now a bit dated, this article was published in the second volume of the book Architecture of Open Source Applications and provides a little more context for the architecture of Matplotlib. Now, in previous versions of Matplotlib, we would use a backend style for Jupyter called nbag. But things have changed, and now we use an inline backend engine. Now, you don't really need to know all of the details of this, but it's helpful to know that you can investigate this if you want to. So let's import Matplotlib and check which backend we're going to be using today. So here I'm going to import Matplotlib as MPL, and then I'll just run get backend. And you see it tells me which module I'll be using, and today we're using this backend inline module, which is the normal one that you would use in Jupyter right now. Okay, we're going to start our plotting journey by making a graph using the plot function. A plot has two axes, an x-axis along the bottom and a y-axis which runs vertically. First, let's import the PyPlot scripting layer as PLT. All of the functions which we're going to run against the PyPlot module are part of the scripting layer of the architecture. Let's take a look at the plot function by looking at the doc string. So here I'll just import as PLT, and remember we can look at the doc string of any function we want just by adding a question mark afterwards. Now when we run this command, Jupyter's actually going to go and look up that doc string for us and show it here. And so you can see this is the method signature, plot.plot, and we've got star args, scale x, scale y, and we see this star kw args, keyword args, and then it gives us whatever the developers have written here for the doc string. And for this one, it's actually quite extensive, and it mirrors what you would find in the online documentation as well. Okay, that's a lot of documentation. If you're not used to seeing it, this Python function declaration with two arguments, the star args and the double star keyword args, can be a bit obscure. What's being said here by the star args is that the function supports any number of unnamed arguments. The double star keyword args also means that it supports any number of named arguments. This makes the function declaration very flexible, since you can pass in basically any number of arguments, named or not, but it makes it difficult to know where there's an appropriate argument that you should be using. Reading on, we see that the arguments in this case are going to be interpreted as XY pairs, so let's start there. So let's try with just one data point at position 3, 2. The return value is the plot itself, and Jupyter Lab's going to actually display this automatically on its own and render it in the notebook. Okay, we don't see any data points though, which is a bit odd. It turns out that the third argument to plot should be a string, which signifies how we want that data point to be rendered. Let's use a period. This means a dot, and we'll see that our data point now shows up. And so the docs tell us what the different characters will render like, and here we're just going to use this full stop or period for the marker. You'll notice that the subsequent calls to plot have not updated our previous visualization. The backend that we're using is not interactive, so these subsequent calls create new plots as new cells in the notebook, and this is a handy way to iteratively explore your data. Here's where some of the confusion with Matplotlib as a library tends to come from. In the last lecture, I explained that there's this artist layer and that it has figures with subplots and axes and data points, and they're all rendered as patches onto these axes, but we haven't actually seen any of that here. Instead, we've just got one function on a module named plot. So what's going on? Well, the pyplot scripting interface is managing a lot of these objects for you. It keeps track of the latest figure of subplots and of the axes objects. Moreover, it actually hides some of the details of these methods on its own. So the pyplot module itself has this function called plot, but is redirecting calls to this function to the current axes object. This makes for a significant learning curve, and you'll see many discussions in web tutorials and on Stack Overflow where people are confused about these two different approaches to make figures show up. In data science workflows, I think it's much more common to use this scripting layer, like we just did. But it's worth it to take a moment at the alternative object-oriented approach that's a bit more verbose. Actually, while some would call this the Matplotlib object API, I think it's more accurate to actually think of this as directly interfacing with the artist layer instead. So I'm going to do a little demonstration here. First, I'm going to import a new backend called the figure canvas ag, and then bring in the figure object. And this is the top level object that we're going to be using. I'll just create a new empty figure, and you can just call figure with empty parentheses. And then I'm going to associate this figure with the canvas backend. And so I can do that just by calling figure canvas ag and passing in the fig. Then we can add a subplot directly to this. We're going to talk more about subplots in a future lecture, but this number here, this 111, that actually just means that we want to add one plot. The return value for a subplot is the axes object, which contains methods for plotting, and we usually call that AX, and you'll see that that's pretty common. All right, now we can actually get to plotting, and we can plot on the axes as per usual. So we just call ax.plot, and we pass in the parameters there. And then finally, we have this figure, but our backend isn't actually able to render this directly within Jupyter Lab. Remember, our backend here is this figure canvas ag. So we actually have to save this to a PNG file, a ping file. And so I'm just going to call canvas.printPing. So after you execute that, you don't really see anything. All these objects have been created, but they haven't been rendered anywhere except for in a file. So what we could do is use this quick HTML cell magic and execute that to see the rendered image. This is a lot more work than using the scripting layer, but you can see here that the effect is the same. So to use an HTML cell magic here, we just put %HTML at the beginning of the cell, and that tells Jupyter to render the rest of this code as HTML. And here I'm just saying create a single image element and render it. And we can see that that image is exactly the same as our previous one. It's important to note that the scripting layer isn't magic. It's just doing some of the behind-the-scenes work for us. For example, when we make calls to pyplot's plot, the scripting layer actually looks to see if there's a figure that currently exists, and if not, it creates a new one, and then it returns the axes object for this figure. We don't have to store any of that though, because we can always get access to the current figure using this GCF function, which stands for get current figure. Similarly, we have another function called GCA, get current axes, which will return to us the current axes to render upon. So let's create a new figure with pyplot, grab the axes, and set some XY limits. So just as we did previously, I'm going to call plot.figure. This is going to create a brand new figure object for this cell. Then I'm going to plot here 3, 2, that point, and this time I'm going to use a circle marker just to show you, how this syntax changes. Now, if I want to get access to the axes there, I call plot.gca. That's going to get the current axes of the current figure and return it. And we usually call that AX. And then I'm going to set some properties of that just for a demonstration. So the function that I'm going to use is called axis. There's a lot of, by the way, of axes, axis in this lecture, so hopefully you'll be able to follow here. But this function actually takes 4 parameters, a minimum value for x, which we're going to put as 0, a maximum value for x, I'm going to put that as 6, and a minimum and maximum for y values. And so we can see here that the dot now is rendered. It looks a little bit different, and we can see if you look back, your axis values for both the x and y have been constrained. All right, one more demonstration on the fundamentals of putting together a plot. You can add artists to an axes object at any time. Pyplot's actually doing this for us when we call the plot function. It's determining what shape we want from the string, the location associated with that shape, and it's creating a patch object and adding that to the axes. If we make subsequent calls to the plot function before we render it, the data is actually going to be added as a different series and colored appropriately. So I'm going to create a new figure. I'm going to plot one point here at 1.5, 1.5 with the circle marker, and then I'm going to add 2 more points right underneath. So I'm just calling subsequent calls to this plot.plot. All right, so you can see here that we now have 3 different points all in a line, and that our axes are constrained to fit this data. A lot of complexity is hidden from you, but you can go even further with the axis object, to the point where we can actually get all of the child objects that the axis contains. We can do this with this getChildren function, and I just want to show you what this looks like because I think it's pretty interesting to know that this exists, even if you're not going to be using it all that often. So if we want to get the current axis of the current image, we can say plot.gca. In this case, a new axis object is being created. This is a new cell. And then I'm going to add a point at 1.5, 1.5. And then I want to take a look at that axis and see what all of the children look like. Okay, so you can see that for this image, we actually have a number of things. We've got a line 2D, a bunch of splines, an x-axis, a y-axis object, and you can look up every single one of these in the documentation. So in this case, our line 2D object contained in the axis, this is actually our data point. We also have these splines, which are actual renderings of the borders of the frame, including all the tick markers, two axis objects, and a bunch of text, which are the labels for the chart. There's even a rectangle, and that's actually the background for the axis. All right, so that was a whirlwind tour of how to be productive with Matplotlib and make your first chart. Now, in truth, you're not going to spend a lot of time getting individual artists or interacting with splines, probably. But you can if you want to. The system isn't magic, and we've walked through how you can investigate a bit better to understand what's actually happening underneath. In the next lecture, we're going to go through some of the different built-in charting options which are available to us in Matplotlib. In the previous lecture, I introduced the plot function, which generates a series of points which get rendered against an axis object. Matplotlib actually has a number of useful plotting methods in the scripting layer which correspond to the different kinds of plots we might want to actually use. Now, we're not going to go through all of them here, but we're going to touch on a few of the major ones. Regardless, there's a few things to keep in mind that we learned about in the previous lecture. First, PyPlot's going to retrieve the current figure with this function GCF, getCurrentFigure, and then get the current axis with the function GCA. PyPlot is keeping track of all of these axis objects for you, but don't forget that they're there and we can get them when we want to do something with them. Second, PyPlot just mirrors the API of the axis objects. So you could call the plot function against the PyPlot module, and this is just calling the axis plot functions underneath. Finally, remember that the function declaration for most of the functions in Matplotlib end with an open set of keyword arguments. There's a lot of different properties you can use to control these keyword arguments, and you're not going to find them described for each function in the docs. This can be a bit frustrating because you end up just having to learn from examples. I'm going to start peppering in some of these arguments this week to demonstrate the Matplotlib documentation and the value of it. And you could take a look at that documentation for each function using this question mark. With that in mind, let's move on to talk first about scatter plots. A scatter plot is a two-dimensional plot similar to the line plots that I've shown previously. The scatter plot function takes an x-axis value as the first argument and a y-axis value as the second. If the two arguments are the same, we get this nice diagonal alignment of points. So just as before, I'm going to bring in matplotlib.pyplot as plot and bring in that scripting interface. I'm also going to bring in numerical Python, and we're going to use this later. Matplotlib is actually really based on these NumPy arrays, and so you see a lot of examples with this. First thing I'm going to do is create some fake data. I'm just going to create this. I've got this list of 8 data points, 1 through 8, and I'm going to create an array out of it, and then I'm just going to make it symmetrical. So I'll just have this y value, which is the same as x. Then I want to create a brand new figure for this cell, and then I want to get Matplotlib to produce a scatter plot. And this is similar to the plot.plot function, but underlying objects in this case are not line 2Ds. Okay, so we can see this nice arrangement of points, symmetrical, nice diagonal, 1, 2, 3. The x-axis and the y-axis have been constrained automatically by Matplotlib to fit our data. Now, scatter doesn't represent items as a series as plot did. Instead, we actually can pass it a list of colors which correspond to given points. Let's use some basic list arithmetic to create a new list just short of the number of data points we need and set all of those values to green. Then we'll make the final point red. Okay, so we use the same data, 1 through 8. Now, I want to also make this list here, green, 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 all the way, and then the last one red. Now, I could have just hard-coded this list in here. I wrote it in the docs so you'd be able to see it. But you could also take just a list of one element, green, as a string, and times that by the length of our data minus 1. And that's going to create 7 of these green elements here. And then I can just append to it a red. So I just want to show you, you can use the normal numerical Python arguments here. Then we're going to create a new figure, and then when we call scatter, this time we're going to put in the X and the Y. I'm going to show a new parameter here, S for size, and then I'm going to pass in our list of colors that we want for those points. All right, so we see that we've got all of those points. They're a little bit bigger. They're all green except for the last one, which is red. The separation of data points into lists is actually a pretty common pattern in Matplotlib. You have some set of items, but they're actually described as the same slice across many different data sources. Those who are familiar with object-oriented programming might expect that each data point is actually represented with its own instance, which encapsulates all of its properties. For instance, a point has an X value and a Y value and a color and a size. That's not the case here. This is where it's useful to have some knowledge of list comprehensions and lambdas, as we talked about in the first course. Also important is the zip function and list unpacking. And because this is so common in the Python data science world, I'm going to take a brief aside and talk about that here. Recall that the zip method takes a number of iterables and creates tuples out of them, matching elements based on the index. So if we have two lists of numbers, zip will take the first from each and create a tuple, and then take the second from each and create a tuple, and so on. Also remember that zip has lazy evaluation because it's actually a generator in Python 3, and that means we need to use the list function if we want to see the results of iterating over a zip. We call this realizing the generator. So let me demonstrate that. Here we're going to create a new zip generator with a zip function passing in two lists of numbers. When we convert this generator to a list, we'll see that there's a list of pairwise tuples. So I've got two lists here, 1 through 5 and 6 through 10, and I'm passing them into zip. And the return of this is actually a generator. And then here I'm going to print the list of that generator. And this realizes the generator. It actually runs through the generator and creates the new list, and it will create this output. Now, we can do that again, but this time we can use unpacking instead of list. So I've got the exact same generator function. I've created the exact same generator, but this time I'm calling print and I'm taking zip generator star. In this case, it actually unpacks that collection into positional arguments. You see that we get all of those same tuples, 1, 6, 2, 7, 3, 8, but they're not a single list. They're individual arguments. Let's take a look. Storing point data as tuples is common, and you should be familiar with being able to convert data to and from this form. If we want to turn the data back into two lists, one with the X component, one with the Y component, we can use the parameter unpacking with zip. When you pass a list or an iterable to a function and prepend it with an asterisk, each item is actually taken out of the iterable and passed as a separate argument. Okay, so that's a brief aside on a valuable tool which you'll see a lot when manipulating and cleaning data in the wild in Python. Now, let's get back to plotting. Let's take these two lists and plot them as a new figure using scatter. Instead of plotting them as one data series, we'll slice the lists and plot them as two data series. Instead of setting a color per data point, like I did previously, we can color each series with a single value if we want to. We can also do things like change the color or transparency of an entire series. And we can add descriptive labels, of course, as well. So in this example, I'm going to create a new figure. Then I'm going to plot a data series, tall students, in red, using the first two elements of X and Y. So I just take our X variable and our Y variable from before. And remember, this is the slicing notation. It just takes out two elements, the first two elements. I'm going to set the size to 100. I'm going to set the color to red. This is going to color all of the items to red if you pass it in just a single item like this. And then I've set a label, tall students. And then I'm going to do the same thing for the short students here, but it's actually from the second element onwards. So that's actually the third position, right? Because we index at 0. And I'm going to make it blue. Let's execute that. Okay, so we can see here in the image that we have two tall students that are red, and then we have all of these short students that are blue. You'll notice that the label didn't show. At the moment, it's actually just held internally for each series, and I'm going to get to that in a minute. But let's talk a bit more about the properties of an axis instead. The axes generally have labels to them to explain what they represent or the units that they describe. Charts tend to have titles as well, so let's put this in place. Since pyplot mirrors much of the API of the axes object, we can make these calls directly on the pyplot object. So I'm going to do the exact same thing, create a new figure. I'm going to create our two scatter points. And now if I just want to add a label, I'm going to add the label, the X label. And so that'll appear at the bottom. The number of times a child kicked the ball is what I wrote here. And then we can add a label to the Y-axis as well. And so we could just use plot.xlabel, plot.ylabel, and plot.title for these. Underneath, what's happening is plot is calling GCA, get current axes, and then calling the set X label and set Y label. Okay, let's add a legend as well. You'll see that Matplotlib is going to place our legend in the upper left-hand corner, and it's going to put a little bit of visual information there about our students. So we have the exact same code here. I've just copy and pasted it, but here I'm going to add the legend. And to do that, all we do is call plot.legend, and it indicates that we should add that legend and use the labels that already exist on the data underneath. So if you have those labels there, Matplotlib is going to use them. If you go to the docs for the legend, you'll see that there's a number of different parameters, and one of them is called location. And a value of 4 will actually put it in the lower right-hand corner of the axes. Now, we can also get rid of the frame and add a title and do any number of different visual transformations. So I've taken the exact same code here, and now for the plot.legend, instead of telling Matplotlib to just do whatever with it, I'm setting the lock for it to 4. I'm saying I want the frame off, so frame on equals false, and I'm setting it a title for the legend. Now, all of the things I've been showing you are renderable objects associated with the axes. The legend, for instance, is an artist, which means it can contain children. Let's take advantage of this and write a little routine to recursively go through the list of children in an artist. So this is a fun activity I like to do to really demonstrate how Matplotlib is working underneath. So we're going to import the artist class from Matplotlib. And again, you're not going to do this when you're doing your regular data science, but sometimes you want to debug essentially a chart or a figure, and you want to really understand how it's being built underneath. And I think this is really powerful. So we're just going to make this recursive function called recgc. It's going to take in some artist and some depth parameter. It's going to check if the object that's been passed in is an artist, and if so, it's just going to print out its name, and then it's going to recursively call itself using getChildren. And so we're using some fun stuff here. We're printing out a couple of spaces, and then the depth, and then whatever the artist name is. So we'll get this nice indented list. Okay, so finally, let's call this function on the legend artist and see what the legend is actually made up of. So you can see that that simple little legend, a little title, a little box, and a couple of dots, that as an artist is actually made up of a number of different offset boxes for drawing, as well as text areas and path collections. What I want you to take away from this is that there's nothing magical about what Matplotlib is doing. Calls to the scripting interface just create figures, subplots, and axes. Then they load those axes up with various artists, which are the back-end renders put to the screen or some other medium like we looked at as a file. Now, while you're going to spend 95% of your time at the scripting layer, happily creating charts and graphs, it's important to understand how the library works underneath for the other 5% of the time. And the time that you're going to use this is when you want to have really fine-grained control over and to create your own charting functions. And you're going to have a chance to do that by the end of this course. In the next lecture, we're going to go back to line plots and create a few more and then onto bar charts. Okay, on to line plots. Now, we've actually seen line plots a couple of times, but they looked like scatter plots. In fact, the very first plot I showed you was a line plot, because we create a line plot with the plot function, and it renders a number of different series of data points and connects each one in a series with a line. In the very first one I showed you, I only had 1 point, so you didn't see any lines. Let's jump right into this. There's a couple of things which are new about this versus the scatter plots we just saw. First, we only gave y-axis values to our plot call, no x-axis values. Instead, the plot function was smart enough to figure out what we wanted and to use the index of the series as the x value. This is pretty handy when you want to make quick plots. Second, we see that the plot identifies this as a 2 series of data and that the colors of data from the series are different, including the data points and the lines between the data points. This is different from the scatter plot, which required us to label those lines directly. Okay, so I'm going to import matplotlib pyplot. Now, we can use NumPy to create a linear series of data points 1 through 8. We'll also create a number of quadratically increasing values as the second series, just for a demonstration. Remember, you can use broadcasting in NumPy to do this, so you'll often see this and want to do this for quick demos. This is just our nice little array here of 8 points, and then here we're just going to square it to create that exponential data. This time I'm going to use the mini formatting language to describe how I want those markers and lines to be rendered. So previously you saw me use this O and it just made this circle marker, but we can prepend that with a dash to use a solid line between the circle markers. Note that I'm passing the data followed by the formatting for each series. So we're going to see the result as a 2 data series, the linear one at the bottom and the quadratic one at the top. So this looks a little odd and a little different, and it's worth studying this for a moment. Here I'm calling plot, I'm passing in our data, I'm telling our plot how it should render our data, then I'm passing in another piece of data, and I'm telling it how to render that. And we can just keep doing this for as many series of data that we have. All right, so we can see those two pieces of data, the quadratic and the linear, being plotted there. Now, it's pretty easy to extend this and add an arbitrary new line. So for instance, I'm going to use this --r, which tells plot to add a dashed line in red. So here I'm going to have the exact same plot call, linear data, exponential data, -o, but then I'm going to actually make a subsequent call to plot, and I'm going to pass it in these 3 points, and I'm going to say --r. Do I have to put this on a subsequent line? No, I could have just added these as extra parameters here. I just wanted to show you that you can do that. Right, and so now you can see that we've got our two first series of data points, but now we have this third series that has essentially no markers, and it's just got dashed lines throughout. Did you notice what I did there, though? I didn't call plot.figure. By default, PyPlot scripting interface will call plot.gcf when you try and do something. If there's no figure, then it's going to create one for you. The way JupyterLab is configured by default, it will automatically close a figure after each cell is executed. So this means that PyPlot is going to create a new figure for us each and every time. This is a great time saver. Goodbye plot.figure. We can use the regular axes functions creating labels for the axes and the figure as a whole as well. And we can create a legend too. But since we didn't label the data points as we did with the scatter plot, we need to create legend entries when we add the legend itself. So I like to label my data points when I actually add the series directly, but you don't have to do that. So I want to show you because you'll see lots of different examples with this. And of course, the ordering for most of these, it doesn't really matter because it's setting these axes object before it's actually rendering. So here I'm going to create an X label, a Y label, and a title before I actually have any data. In fact, the very first one here is going to create a new figure and a new axes object and set the label before we've done anything. Then I'm going to add a legend, and I'm going to say, well, the legend's got 3 things in it: baseline, competition, and us. And then I'm going to do the exact same plot calls that you just saw. And you can see it renders here nicely, and we've got the sum data, we've got the some other data, and we've got the title. This is a good time to introduce the fill between function of Matplotlib. Now, this function isn't specific to line plots, but you can see it commonly used with line plots to highlight an area, so I want to introduce it here in this context. Let's imagine that we want to highlight the difference between the green and the blue curves somewhere. We could tell the axes to paint a color between these series using the fill between function. So I can have that same code, X label, Y label, title, legend, plot. And then now we actually need to grab that current axis object and then call fill between. Now we didn't specify any X values in our call to plot. Remember, by default, it's just going to use the indexes of your list or your array that's passed. So I'm actually just going to use the same range of data points that it's already using, which is symmetrical. And then we're going to put this as our lower bounds and our upper bounds with the color that we want painted. And for fun, I'm going to add a transparency. So here I'm saying, PyPlot, get me the current axis, then call on it, fill between. I want you to create a range from the linear data, so a bunch of numbers. That's our X values. Here's our then linear and exponential data. And I want you to set the color of this fill between to blue, and I want you to set the alpha to 0.25. And the linear and the exponential data are going to show the the lower and upper bounds of this, respectively. Okay, so that renders nicely. We've got this blue line, we've got the orange line, we've got the points, and we've got this nice fill between shaded area, and we have all of our title and so forth. Our charts are really becoming a little bit more sophisticated in how they work. So let's try working with dates. Most likely you're going to have a series of X values and Y values which you're looking to plot. Often with line plots, this comes in the form of a date time on the X-axis. Now, in earlier versions of Matplotlib, it was painful, and you could go back to maybe a previous lecture video that I taught on this. But actually, I've been able to shorten this quite a bit because Matplotlib is growing quite a bit. So let's change our X-axis here to a series of 8 date time instances in 1-day intervals. So I'm going to use the NumPy arrange function here, which we saw previously, and you'll commonly see this in Stack Overflow questions or textbooks or just example videos like this. And I'm going to ask for an arrangement of dates at daily intervals. And so I give it the start date and the end date as a time, and then I set the D type to be date times 64. And then arrange is going to create that arrangement there. Now, I'm just going to replot our linear and exponential dates. So we have our observations, our linear date, our observations, and our exponential date.
Again, this can be very unfamiliar for people who are not used to positional parameters. Previously, we had data formatting and then data formatting. Now, because we want to have these dates along the bottom, we have those dates, data formatting, dates, data formatting. So the position of the argument to plot is changing with the number of arguments that we specify in the format of those arguments. This is very unorthodox in a lot of programming languages, and including in a lot of Python, but it's supported in Python, and it speaks really to Matplotlib's roots in MATLAB. Okay, this produces a pretty decent looking figure with the date that we want. The dates overlap pretty heavily. Now, there's a couple of things that we could do here. For instance, everything's from 2017, so we could take the easy way out and just iterate through and change the labels by stripping off the year and then add an x-axis label which clarifies this is all for 2017. This is pretty reasonable, but I want to show you a couple of features of Matplotlib and how we can deal with text instead. There's lots of interesting properties of the axis object, and you should use some of them in the assignment, and I encourage you to go to the docs and explore them now that you're starting to pick up some of the skills and understand how to build those basic plots. For instance, you can get the grid lines, the tick locations for both major and minor ticks, and so forth. Just like all artists, an axis has a bunch of children which are themselves artists. In fact, if you're following along in the Jupyter Lab notebook in Coursera with this lecture, why don't you just pause the video and run that recgc function we wrote earlier to explore what kind of artists are on this x-axis object and what it actually contains. What I want to show you, though, is that you can access the text of the ticks using the getTickLabels function. Each of the tick labels are a text object, which itself is an artist, and this means you can use a number of different artist functions, and one specific to text is to be able to set the rotation function, which allows the rotation to be set in degrees. So let's iterate through the axes labels and change each one to rotate it. Okay, so here's just our plot data as normal. Now I want to grab that x-axis, so I just grab the axes object, that's plural of axis, and then grab the x-axis, and then for each item inside of there, I want to get the tick labels, and I want to set that rotation to 45 degrees. All right, so that looks pretty easy. It was quick, pretty fluid to do, and you can imagine how we could customize this further if you wanted. So let's add back in our headings now. So the exact same thing, but now I've added to the bottom our labels, X, Y, and title. I tend to add my labels at the bottom, but that's just habit. As you saw earlier, you can add those whenever you would like to. All right, there we go. Wonderfully readable dates in Matplotlib. And while we're talking of text and readability, let me share two other insights. The first, dealing with equations. Matplotlib has a fairly strong connection to LaTeX, a typesetting language used by mathematicians and scientists. This means that you can use a subset of LaTeX directly on your labels, and Matplotlib is going to render them as equations. Here, for instance, we could set the title of the axis so that there's an x squared directly in it. To do this, we escape to LaTeX math mode with $signs. Note that this works regardless of whether you've got LaTeX installed or not. For a long time, you wouldn't have LaTeX installed on Mac OS or Windows. But with a full LaTeX installation, you actually have significant control over the text formatting. For the second insight, I want to talk about the size of the figure itself. Why are we looking at these small postage stamp figures? Well, that depends on your screen size and resolution, but the point is we can tell Matplotlib that we want the figure to be a certain size by passing in parameters when we first make that figure. So in this next example, I'm going to specify it in inches, but there's various other dimensions that you can use. You can set them as centimeters or DPI and so forth. So I'm going to create a new figure, this time explicitly, but I'm going to pass in this fig size keyword argument as a tuple, and I'm going to make it 8,6, which means 8 inches by 6 inches. Then I'm just going to put in my usual data here from above, so this is basically copy and paste from above. But I wanted to show the title here. When you want to escape into LaTeX math mode, you can just put the $sign and then put inside of any text formatting string and then put what you want. So this in LaTeX means x to the power of 2. You don't have to do this, right? And LaTeX itself is a huge learning curve in and of itself, but for basic formula, it's quite nice, and you can, of course, do much more extensive things if you're in a scientific industry. That's been a pretty successful look at Matplotlib basics, I think. From the architecture overview to creating clean charts we could include in a report or just on our own through data explorations. I want to show you one more thing this week in the next lecture, the bar chart.
Matplotlib has support for several kinds of bar charts. In the most general case, we can plot a bar chart by sending in a parameter of x components and a parameter of the height of the bar. So let's do this now with a little bit of linear data. Okay, so we bring in our regular libraries for pyplot and numpy, and then I just create our linear data. Now I'm going to generate a list of the X labels, and in this case, I'm just going to have a whole bunch of numbers here, just the exact same as the data, but you could make these whatever you want. Then we pass this in with the linear data as the bar heights. So we have the X values. These are going to be the actual values along the X axis. The linear data is actually the height of the bar. So in this case, it's going to be this increasing step size from 1 to 8. And then the width of the bar. And I'm going to set that width to 0.3. Okay, so we can see here that we get nice little blue bars. They start at 0 and they go all the way up. And we can see that the 0th item is actually a number 1 in its height, right? Because the array that we made is 1 through 8, but then we used a range, and NumPy range looks at the size, right? Because we used this range function. And so it did 0 through 7 for our x-axis labels. To add a second bar, we simply call this bar plot again with new data, keeping in mind that we need to adjust the X component to make up for the size of the first bar that we plotted. So you'll get to feel my frustrations around this shortly. So let's get some new X values, and then I'm just going to make this exponential. I'm going to take our linear data and square it, and then for the new values, I'm going to add these items plus 0.03, right? So I'm building in this little offset for each one of those. Then I just call two calls to bar, plot.bar. So the first one is going to be our original data. The second one is going to be the new data, the new values, but I'm going to use the same width of 0.3 and the color is red. Okay, so we see our linear data, and then we see our exponential data. So the plot looks okay, but not great. All of the X labels are to the far left of the items being described and not centered. Now, we could center them with a given bar using this align parameter, but it's a bit frustrating when you have to have multiple bars, and then you have to calculate it all by yourself. And it's a pain to go through and add new data series manually. This actually gets worse. We actually have to manually iterate through and add in dates if we want them as well, because otherwise we wouldn't be able to set the left bar location properly. I'm going to be honest, bar charts are one of my least favorite things to create in Matplotlib. I feel like the foundation is there, but in some of the ways I want to use the API, such as just plotting several series of data in groups across time, these are sadly missing. There's some other nice features of bar charts, though. For instance, you can add error bars to each bar as well using this y_error parameter. For example, each of the pieces of data in the linear data might actually be a mean value computed from many different observations. So we could just create a list of error values that we want to render as well and show those as error bars. Let's take a look. So I'm just going to import this random function, randint. It's going to generate random integers, and then I'm going to use a list comprehension here. Now you'll see list comprehensions a lot in examples, and it's good to make sure that you know how to read that syntax in Python. So this says, when we use the indexing operator in this way, or the square brackets, it says create me a list, and inside is our algorithm, if you will, for the list. So call randint 1, 4, so create a random integer between 1 and 4 for x in range, and then we set the size of our range here. And this is going to plot now the error bars. So we just have our X values, our linear data, just like before, our width, and then here we could just set the Y error and to this linear error. So that's going to be the numbers between 1 and 4 inclusively here. Let's take a look. So that's kind of nice, right? And you can see actually in the example that I ran, and of course yours might be different, right? Because we're using random numbers. In the example I ran, one of the error bars actually goes beyond the bottom of our chart, the 0 in the x-axis, and that's fine. Matplotlib just adjusts things for us automatically. Now, we can do stacked bar charts as well, and this actually works better because you don't have to deal with all the fidgety positioning arguments. So for instance, if we wanted to show cumulative values while also keeping the series independent, we could do this by setting the bottom parameter of the second plot to be equal to the first set of data to plot. So you plot one piece of data, and then you plot the second piece, and you can just use one parameter to set the bottom for each of those bars as the heights of the previous one. So here I've got this range of values. I plot our first data, the linear data, and here I'm going to color it B. And then for the next set, the exponential data, I'm going to use this bottom keyword and set it to the linear data. Remember, these linear data, these are the heights, right, in order. And the x-vals are the first parameter. So the x-vals are the same for these two series. The linear value heights and the exponential heights are different. And for the exponential data, I want their heights to start at the bottom of the linear data on an item-by-item basis. And I'm going to make that one red. Finally, we can pivot this bar graph into a horizontal bar graph by calling the bar h function instead. But note that we've got to change the bottom to a left and the width to a height, right? So our language changes as we pivot things to the side. So to switch to horizontal bar charts, we just use bar h as a function. And now we just change our height to width, or rather our width to height here, and we change our left to the linear data instead of the actual bottoms. Okay, and so that's a very basic stacked horizontal bar chart. All right, those are the basics of charting and plotting in Matplotlib. I think it's important to realize there really isn't any magic going on here, and that's one thing I think you'll be able to take away from my lectures. The scripting layer is really just a set of convenience functions on top of this object layer. Some people have a preference for one or the other, but at the core they manipulate the exact same data elements. And I don't think you should think of them being as opposed in one way or duplicative. They work together, and being able to move back and forth is really important. I would say that in general, a data scientist is going to be using that scripting layer regularly. It's certainly what I do. Now, we've talked about some fundamental charts in this module: scatter plots, line graphs, and bar charts. There are more, and we're going to dig into some of those in the next module, more advanced ones. But I think these are a good base for consideration. The assignment for this module is a tough one. It's meant to show you real-world data visualization problems. You're going to have to leverage your knowledge of the pandas library from the first course and couple it with your new knowledge of Matplotlib to come up with an elegant solution. But the final result should be a portfolio-ready piece. So I'll see you in the forums for discussions and for help. In this lecture, I want to walk you through the process of taking a regular Matplotlib plot and applying Tufte's principles of data-ink ratio and chart junk to make it just a little bit better. I'm going to walk through all of the steps using the Jupyter notebooks, and you're welcome to follow along. But if you want a bit more of a challenge, I'll be including in-video quizzes along the way with prompts to help you consider the problem, and you can solve it before I address it. Now, I think that the chart junk and data ink ratio are incredibly important, and so do the Matplotlib designers. In fact, Matplotlib has evolved significantly, and you've heard me mention this before, from the first time I taught this course into the current iteration that you're seeing now. And a lot of what I had to do then, I don't have to do anymore, because there's new, what we call sensible defaults or good defaults. But still, there's some things that we can do, and your knowledge of the axis objects, your knowledge of the scripting and the object layer, your ability to go to the documentation and problem solve and identify what components you want to change really gives you a lot of power to customize a plot in the way that you want. So let's get started. We're going to use a plot of data on the popularity of programming languages from Stack Overflow, and I'm actually using the data from 2016, which is the data I originally used when I was teaching this course 5 years ago. All right, so we're going to import matplotlib.pyplot as plot and import numpy. So there's actually 5 different languages that are being considered here: Python, SQL, Java, C++, and JavaScript. And you can go to the URL and find their positions, and we're going to use that as a rank in numpy as the range function. And you've seen me do this in some of the examples. And I've hard-coded here the popularity values. So the first one is 56, the second one's 39, the next one's 34, and so forth. So I'm going to have the languages. These are my labels. I'm going to have the positions. This is the X position arrangement, and then I've got the popularity. Now I'm just going to create a bar chart based on the rank, right? So I'm creating a new figure. In this case, I've decided I want my figure 10 by 8. I'm creating a bar, so I pass in the X value positions, then the height, which is the popularity, and then because I only have a single bar and I don't have multiple series, I can align the text underneath, which is kind of nice, and then I can set my X ticks, my Y label, and my title, just basic good chart things. All right, so that's what you get when you run it just out of the box. So here's the first challenge. Our plot has this frame around it, but it's not really necessary, and it seems a little heavyweight. So let's follow this data ink ratio of Tufte's, and let's remove that ink. This is a bit more involved, but you tell me how you would try and do it on your own. All right, the way I'm going to solve it is to get the current axes, then I'm going to iterate through all of the splines, and I'm going to set their visibility to false. They're still going to be there, just not be found. They'll still be there as objects, they'll not be rendered, so I'm not setting it to transparent, and that's another way you could approach this, actually, that would be kind of interesting. I think you'll find that already this is going to make the chart look a little bit more lightweight. Okay, so we've got the exact same code, and then just at the bottom here, I'm gonna go get the current axes. I'm gonna get the splines for the axis object. Remember, this is both the X and the Y axis, right? GCA is axes plural. I'm gonna go through the splines, I'm gonna take their values, and I'm gonna set the values there to false, the set visible to false. Okay, so that's good, but not really a huge change. But the blue, it's kind of nice. I like the blue, but it doesn't really help us differentiate between the bars at all. I mean, we're comparing all of these bars together, but they're all blue. So how about we soften all of the hard blacks to gray, and then we change the bar colors to gray as well. But let's keep Python, the top language here, the same blue that it was originally to make it stand out. So I'm going to do the exact same code as before, but the change is right here. I'm going to take that very first bar, right? Now when I do plot.bar, it's going to return to me this collection. And I can grab that first item in there, and I can set its color to this nice bright blue, a Python blue, if you will. And you'll note that I've set the color of the other bars automatically to slate gray here. And then, of course, I want my titles, I want my alpha transparencies, and I want my spline values here. Okay, so that's what that looks like, right? We can see clearly one is being compared to everything, but we can still see all the heights of everything, and we can reference both on the x-axis and the y-axis, and it feels nice and light, nice and airy. It's got a low ink for data ratio. But let's tackle that y-axis. Why don't we just remove it, and why don't we directly label those onto individual bars? And you saw that was one of the principles that we could be using to better label our data. No need for a person to have to look at the y-axis and try and scan over and try and guess at the height. Why don't we just move that value directly there? So how would you go about doing it? Why don't you pause the video and take a shot? Here's how I'm solving it. So I've got the exact same code here. I've got my X ticks, but here I'm just going to get rid of the Y ticks. There's not much I actually have to do to hide the Y tick values. I just pass in this empty list, and it's going to set those values to nothing. And so it's just going to get rid of them. So removing that label is easy, but changing the bars, that's a little bit more of a pain. So for this, I actually want to iterate over each of the bars and grab its height. Then I want to create a new text object with the data information in it and render it to the screen. So it's easy to get the height from the bars. I mean, we already know that. We fed that in. But this means that we have to play a little bit with padding. And anytime you have to deal with text, unfortunately, there's a little bit of annoyance with that. So you have to be cautious, and you have to be willing to decide how much pixel peeping you actually want to do. Here, I'm going to set the X location to the bar, X, plus the width divided by 2, and the Y location to the bar height, minus 5. So there's a lot of this that goes on when you want to massage your charts in Matplotlib. You have to do a lot of this math to render things in your layout yourself. Now, it might seem weird to get the middle of the bar in the X dimension, but that's because I'm actually setting the label to center itself horizontally. Okay, so I get the bar height, I get the current axis, I create text, I take the bar that I'm dealing with, remember we're iterating through the bars, I get its X location plus its width divided by 2, so that's my parameter for X. Then I get its height, and I'm going to just bump it down a little bit, minus 5. Then I'm going to create a label of the string of the integer of the height, because that's actually the data value that I want to have rendered there, right? The height of the bar. And then I'm going to add a percent sign after it, because it was all in percentages. Horizontally aligned to center, color it white, because we know our bars are either gray or blue, and set the font size to 11. So one line of code to create a piece of text that's going to get dropped on the bar, but there's a lot of thinking that has to go on and a little bit of experimenting to make that happen. I think you can agree, though, that this chart looks lots better than the very first one we did. We can clearly see there's a comparison of Python to the other languages. The languages are all being represented, and everybody can see what the different values are for each one of those languages directly. It's very lightweight, very easy to embed into a report or the like. That's all there is really to it. A simple series of steps to make your bar charts a little bit more usable. When you were watching this video, did you find a different way to do it? Did you tackle this in different ways? Perhaps there were other elements from Tufte or Cairo that you think could be used to make this visualization, even simple as it is, just a little bit more readable and intuitive. Feel free to go into the discussion forums and share them with me and your classmates. In Module 1, we talked about principles which underlie good visualizations, and we pulled from work by Cairo and Tufte. In Module 2, we opened up this Matplotlib Python library. We started with the architecture and we worked our way through some of the most common kinds of plots, scatter plots, line graphs, and bar charts. In this module, we're going to do a bit more of a deeper dive and talk about multiple plots with the same figure, interaction, animations, and a few more different kinds of plots that you're going to find useful on your data science journey. Now, if you've been doing the assignments, you've undoubtedly been visiting the course discussion forums, going to Stack Overflow, and reading the Matplotlib API documentation. I want to point you to the Matplotlib mailing list as another great resource for support. There's going to be a resource posted in the course on how to browse that list. Now, it's pretty common with open source projects to have two different mailing lists, one for developers and one for users. The users places where we would go to ask most of the questions about how to use the toolkit. But I really encourage you to take a look at the developer archives too, to get an idea of how this project sort of evolves and get a look behind the scenes. Okay, let's start this module with a deeper look at subplots. Thus far, we've been using a single axis object to plot a single graph or figure. Sometimes it's useful to show two complex plots side by side to visually compare and let the viewer come to their own understanding. Matplotlib handles this within a single figure object. So let's first set our rendering backend to the notebook and then import our pyplot module and numpy, as we're going to need them both. Okay, so I'm going to import Matplotlib pyplot scripting interface and numpy. We're going to use numpy a lot and we'll use pandas as well in this module for generating some data. And then I just want to look at and show you what the documentation looks like. So remember, you can always just put a question mark like I have here after a function if you want to know inline a little bit more what it's about. So we see that rendered here, and we can see that we've got plot.subplot, takes in args and keyword args, and we've got the doc string, and then we can see all sorts of information about the different parameters and what they mean and how to use them. And this should be the same as the web documentation, but it'll be very specific to whichever one you've got installed, so you don't have to try and figure out which version you're using. If we look at the subplot documentation, we see that the first argument is the number of rows, the second argument the number of columns, and the third is the plot number. In Matplotlib, a conceptual grid is being overlaid on the figure, and a subplot command allows you to create and access different portions of this grid. For instance, if we wanted two plots side by side, we would call subplot with the parameters 1, 2, and then 1 as the third parameter. This would allow us to use one row with two columns and set the first axis to be the current axis. So let's do that. Let's create a new figure and then a new subplot with one row and two columns. The first axis object the pyplot will plot against is the left-hand side. So I'm just going to go plot.figure to create a new figure. And then here I'm going to make a subplot. And this is the number of rows. This is the number of columns. And then this is the axis in that set that we're interested in working with. And then I'm just going to plot some fake data here. So this is just a linear array of data. You'll notice I'm using a NumPy array. So Matplotlib uses NumPy arrays for almost all of the data, and that's important. They're not lists of data. I'm actually creating an array, and then we'll just plot this data. Okay, great. So we've got this skinny plot on the left-hand side. Now, if we made a second call to subplot, we could indicate that we also want to plot on the right-hand side. So let's do that. So you see here, I've just copy and pasted things. So remember from our earlier lecture that at the end of every cell, the figure is actually closed automatically by Jupyter. And that might be a little different than some of the docs that you see online, which are showing, for instance, how to use Matplotlib in a traditional application or in a different kind of editor or on the command line. So here, I'm going to create that same subplot, same data, and I'm going to plot it. But now I'm going to get a reference. I'm going to set the active subplot to the second one. That's the right-hand side. Then I'm just going to make our data exponential, and I'm going to plot it as well. Okay, that's nice. Now we've got two plots, each with their own axis object. Now, the norm with Matplotlib is that you're going to store that axis object that you get back from the subplot. But then you can call subplot again, and at any time, the parameters that you're interested in, you can get back to that axis. So you can move back and forth between the axis objects in your scripts if you would like. You don't have to do everything with one axis, then everything with the next, then everything with let's say, the third, fourth, and so forth. Take a look at this figure, though. Do you notice anything odd about this image, thinking in particular of our first week of the course? The two images have different y-axis values. Now, this would be a problem and potentially mislead the reader if we didn't find a way to lock these axes between the two plots. When you create a new subplot, you're actually able to indicate that you want to share the x and y or both axes using the share x and share y parameters. So let's clean this up and try that. Okay, so I'm just going to plot the first figure, and this time I'm actually going to get that axis back. So each time plot.subplot's actually going to return to you the axis that you're referencing. Sometimes you want it, sometimes you don't care about it. This is kind of the magic of working with both the object and the PyPlot scripting interface. So I just want to take that axis, I'm going to plot onto it this linear data, but then down here, what's really interesting here is that I'm actually going to indicate that we want to share the y-axis between this. So I've got this other call to plot.subplot, that's going to return the right-hand side axis object as ax2. I'm actually not going to use that variable anyway. I could just get rid of it if I wanted to. But I've indicated when I set that up that I actually want to share that. Let's take a look at what that looks like. Okay, there we go. Two plots side by side, and we've locked the y-axis, so you actually see the left-hand side plot's been squished down a little bit, and it makes it much more clear that the data on the right-hand side goes much higher. Now, those of you who have been paying close attention will note that I used the subplot function a second time, but I didn't pass in 3 parameters, I just passed in 1. The Matplotlib developers allow you to specify the row, columns, and number of the plot that you want with either 3 parameters, like we did at the beginning, 1, 2, 1, or a single parameter like I did now, 1, 2, 2, or 122. In this case, the hundreds value, is the first argument, the tens value will be taken to be the second argument, and the ones value the third argument. Now, I'm frankly not a big fan of this second syntax. It feels pretty hacky and it really saves on typing 2 commas, but it limits us to a single digit for each one of those. Computer science folks might feel a little twitch inside, like there's something wrong with this notation, and I'll say that I certainly get bugged by it every time I see it. But I want you to be aware of it so you'd be able to read it when you come across it in the wild, whether it be on Stack Overflow or in the docs. An important fact to remember is that the plot location in the matrix of items is indexed starting at 1 and not 0, as would be the convention if you were using something like NumPy. So if you're iterating through a matrix or a list to create subplots, remember to start at position +1. Now, there's a nice function called subplots, and note here the plural, which allows you to get many axis objects at once. And I actually think this is great. You can set up all the subplots you want, you can get references to all those axes, and then you can start filling them in. So if we wanted to get a 3x3 grid with all of the axes, x and y ranges locked, we could do this actually pretty simply. So I'm going to create a 3x3 grid of subplots using tuple unpacking. And it looks a little complex, so let me just walk through it. I want the figure, and then I want a sequence of items, and I actually want 3 items in it, 1, 2, and 3. And each one of those items are themselves a sequence. So when I call plot.subplots 3, 3, indicating 3 rows and 3 columns, I want them to share all of the same x-axis and y-axis. I could, of course, change this back and forth. What actually comes back to me is the figure object, always is my top item, and then a 3 tuple of 3 items in each one, being the axis objects. And this will become a little bit more clear. I'm going to grab this one, AX5. I'm just going to plot that linear data on it so that we can see it. Okay, so the syntax looks a little goofy maybe, since we're unpacking the results of these subplots functions directly, but it's really an effective way to build a grid where everything shares an axis. The results look really nice, but note that this method turns off the y and x labels except for the plots which are on the left-hand side or on the bottom of the figure. This is actually intentional. You're sharing the axes, so Matplotlib's trying to make it a little bit more readable, give you a little bit more space in each one of your plots. Of course, we can actually just iterate through a list and plot one plot at a time, and we don't have to store a reference to the axes if we don't want to. So I'm going to create a new figure. I'm going to call plot.gcf. Remember, that's get current figure, and if the figure doesn't exist, a brand new figure is created for us. Now I'm going to iterate over 6 potential spots in our figure, and I'm going to create a plot with 2 rows and 3 columns. So here I've intentionally set I to be in the range of 1 through 7 instead of 0 through 6. And we talked a little bit about how we index, unfortunately, Matplotlib plots starting at 1, not 0. Now, for this demo, I've just decided that we're not going to plot something if we're in position 5 or 3. I'm just going to leave these as holes so you can see where they show up. So if our I is not a 5 or a 3, then I'm going to add a subplot. Now, in the subplot, we're going to specify the first 2 arguments as the structure we're expecting the figure to take, so 2 rows and 3 columns. The third argument is this floating one. It's the position of the item in the figure. In this case, it's I. And while we're iterating linearly, this is going to be mapped into that 2, 3 column space, right? So even though I is going 1, 2, 3, 4, 5, 6, 7, it actually gets pushed into the 2, 3 space that we've identified that we want our subplot to be. Once I've added that, I just store the result in AX, and then I'm just going to add some text to the figures to make it more clear which item actually went where. And you can look at the lecture on annotation to read more about that, but I'm just going to essentially just convert I into a string value and throw it into our plot. Let's take a look. So we can see here that we have 2 rows, we have 3 columns, and we have numbers in the 1, 2, 4, and 6 spots, not the 5 or the 3. Those are just blank. And here we haven't shared any of the axes, so everybody has their own axes values. So we now understand why there are abstractions of axes in a figure, because a figure might have several axes objects which show multiple views of data. A common data science visual exploration technique is called the SPLOM, which stands for scatter plot matrices. These are particularly useful for getting the relationship between a number of different variables from a quick glance. Now, a SPLOM's actually similar to what Edward Tufte called a small multiple, a set of visuals that look at related data but slice that data into different small visuals so that you can see both the trees and the forest all at once. Let's take a look at a SPLOM. I'm going to make it by hand, and I'm going to use some data from the iris dataset. Okay, let's first capture a list of the variables we're interested in. I'm going to bring in pandas. I'm going to read in the iris.csv file into a data frame, and I've decided that there's 4 columns that I'm interested in. I want to see if there's a relationship between the sepal length, the sepal width, the petal length, and the petal width. And these are all portions and features of a plant, flower in particular. So now we need to create a grid of subplots of the size and width, height equal to the number of different variables that we want to explore. And in this case, it's a 4x4 grid. So I'm going to call plot.subplots. I'm going to say length of columns, and fig size of 1010. I could pass that fig size in, right, to set how big I want my figure because we take that ** keyword args. Now, we want to iterate through each column in our data frame and compare it to each other column in our data frame. I'm going to do this with a couple of nested loops. I'm going to do that by saying for I in range len calls, for j in range len calls. And so this is just our 4x4. And now I just want to plot a scatter plot comparing the columns I and j. Sometimes this is going to be the same column, so we'd expect to see a diagonal line trend there. And I'm going to set the marker size to 5 just to make things a bit more clear. So again, I can just pass that in, and you can check the docs for scatter to take a look. Remember, I've got this axis object back, so I can just say I want this row and this column, and these are the values that I actually want to plot in there. Also, we've seen that we can plot multiple axes things, and it can tend to get cluttered with the axis tick marks and labels. So I'm just going to turn those off just so that we visually don't have to take a look at those. So we don't have to share the axes to shut those off. I can just get the x-axis or the y-axis at any time and set the label visibility to false. Okay, then I'm going to turn them back on only in that last row so that we can see them along the bottom. And so I'm just going to look for when I is equal to the len calls minus 1 and do the same thing for the first column. So let's take a look. Okay, great. We have a nice example of a SPLOM, and we can easily compare the length and width of sepals and petals and look for trends at a glance. One that jumps out to me is that the petal width, the bottom row, has a pretty linear relationship with the petal length, the third scatter plot over. This doesn't seem to be true if you compared the sepal width to the sepal length by looking at the second row and the first column, for instance. In the next module, I want to exploit our new knowledge of subplots while introducing you to a pretty fundamental data science chart, the histogram. A histogram is a bar chart which shows the frequency of a given phenomenon. A great example is a probability distribution. For instance, in the first course of this specialization, we touched on the difference between the random, uniform, normal, and chi-squared distributions. Probability functions can be visualized as a curve, where the y-axis holds the probability a given value would occur, and the x-axis is the value itself. This is called a probability density function. The y-axis values are limited to between 0 and 1, where 0 means there's no chance of a given value occurring, and 1 means that the value will always occur. The x-axis values are labeled in terms of the distribution function. In the case of a normal distribution, this is usually in terms of standard deviations. A histogram is just a bar chart where the x-axis is a given observation and the y-axis is the frequency for which that observation occurs. So we should just be able to plot a given probability distribution by sampling from it. Now, recall that sampling means that we're just going to pick a number out of a distribution, like rolling a die or pulling a single card out of a deck. As we do this over and over, we get a more accurate description of the distribution. Let's quit talking about this and do a bit more coding to see this in action. So I'm going to bring in Matplotlib and NumPy like usual. Now, I'm going to pull some samples out of the normal distribution and plot 4 different histograms as subplots. First, I'm going to create our 2x2 grid of axis objects. In this case, we don't want to share the y-axis between the plots since we're intentionally looking at the number of different sizes of samples. But I do want to share that x-axis. So I've got that in my subplots function, the sharex equals true, and then I've got this nice collection of axis objects. Now, we're mostly interested in how uniform the distribution looks. So we're going to iterate through a list of 4 different values, 10, 100, 1,000, and 10,000. And we're going to pull samples from NumPy. Remember that the normal function of random just creates a list of numbers based on this underlying normal distribution. So if you don't feel confident in distributions for this demonstration, that's okay. Just assume that there is this distribution function that's created, and we're just going to experiment. We're just going to pull some samples out of it. All right, so I'm just going to iterate through each axis. So 0 to len of axes. Remember, I'm grabbing from 0 because that's what our actual list is here, right? We index a list with 0, even though when we're talking about subplots, we start at 1. I'm going to pull out a number of samples, and we're going to get exponentially bigger each time. So this is 10 the first time, then 100, then 1,000, and so forth. And then I'm going to plot that sample on that axis object. And then I'm going to, of course, set something useful for a title. I'm just going to use that sample size. Let's take a look. Okay, there we go. The first plot only has 10 samples, so it looks pretty jagged. In my version here, I don't think anyone would say this is obviously a normal distribution. But when we jump it up to 100 samples, it gets better, but still, I don't know, it looks like it's leaning to the right for me. Yours might look slightly different, right? Because this is a random process. So you should be running this notebook on your own and comparing. It then seems to smooth out a bit on the plots for 1,000 and 10,000 samples. But if we look closely, we can see that the bar of the 10,000 plots are actually wider than those of the 10 or the 100 plots. So what's going on here? Why does the bar on the bottom axis, why does that change? By default, the histogram in Matplotlib uses 10 bins, and that's 10 different bars. Here we created a shared x-axis, and as we sample more from the distribution, we're more likely to get outlier values that are further from our means. Thus, 10 bins for n equals 10 is at best capturing 10 unique values, while for n equals 10,000, many values have to be combined into a single bin. So let's do the same function with the bin width being set to 100, so that we're actually going to have 100 different bins. So the code here all looks the same. The only thing I'm changing is right here, when I actually plot each of our histograms, I'm actually going to say the bins, I want 100 bins along that axis. Okay, so now we see the 10,000 sampled plot looks much smoother than all the others. And the 10 sample plot shows that each sample is basically in its own bin. We only have 10 samples, but we have 100 different bins we're willing to look at here. So they basically all fall in the same bin. So I think this brings up an important question of how many bins should you plot when using a histogram? I'm afraid that the answer isn't actually all that clear. Both of these plots are true. One is a visual of the data at a coarse granularity, and one at a more fine-grained granularity. When we look at the finest grain granularity in our data, plotting with 10,000 bins, then the histogram becomes basically useless for decision making, since they aren't showing any trends between samples as much as they're just actually showing the sample sizes themselves. This is similar to using aggregate statistics like mean and standard deviation to describe a sample of a population. These values are coarse, and whether they are appropriate depends highly on your questions and on your interests. Now, I want to use our newfound knowledge of histograms and subplots to introduce you to the more flexible grid spec layout for subplots. The grid spec allows you to map axes over multiple cells in a grid, so you can make some really custom-looking visuals. For instance, let's create a scatter plot here, where the y values are going to come from the normal distribution and the x values come from a random distribution. Okay, so I'm just going to create some random data here. Our y values are coming from the normal distribution, and then our x values are coming from random. And I'm getting lots of data, 10,000 of these, and I'm just going to, for each one, and then I'm just going to plot that scatter plot. Now, it's not totally clear from looking at this plot what the actual distributions are for each of the axes. But we could actually add 2 smaller plots, each histograms, to make this a bit more clear. let's just dive right into doing this. I'm going to define a 3x3 grid, so 9 cells in total. I want the first histogram to take the upper top right space, and the second histogram to take the left bottom 2 spaces rotated on its side. The original scatter plot that can then take up the 2x2 square in the bottom right. Okay, so to use this grid spec, we first have to import it and then create this new grid spec of the overall shape we want. So I'm going to bring it in from grid spec. I'm going to set my figure size to a little bit bigger, 10 by 10, and then I'm going to create this new grid spec as a 3x3 grid. When we add new items within the subplot, instead of specifying the 3 numbers, row, column, and position, we're going to pass in the elements of the grid spec object which we wish to cover. And very important here, because we're using the elements of a list, all of the indexing starts at 0. So it's very reasonable to use slicing for the beginning or the end of lists. The grid spec is indexed as rows and columns using this indexing operator, the square brackets. So we'll create the first subplot and histogram in row 0, covering off the first element, the middle position, and then go to the end of the row. So here I've decided that it's going to be a histogram along the top, and I'm going to say plot.subplot, and I want to pass in the grid spec elements that should cover. And so it's 0, the very first row, and I want to take 1 till the end of whatever is left in the grid spec. Now, when I want to create that side histogram, I want to start at row 1, but I want to actually continue all the way down to the end of the row elements, but I want to limit it to the 0th column. So here, the side histogram is going to run top down, and so I want it to cover from 1 down as far as the rows, so all of the rows from 1 on. Remember, row 0 is up here in the top histogram, but I only want to look at the first column, so that's a 0 on as the second input to that indexing operator. Finally, this scatter plot I want to be in the lower right. When we execute this, we'll be able to see all of our plots, but I want the scatter plot to be from row 1 down and from column 1 over. Let's take a look. Okay, that gives you a sense as to the layout, but now we got to fill this with some data. First, we want to deal with the scatter plot, and then I'm going to go to the top histogram, which is for the x values of the scatter plot, and then the side histogram for the y values. We want that side histogram to be lined up, so I'm going to rotate the layout by setting the orientation. And there's actually a few ways of doing this, but since it's so common, Matplotlib actually has an orientation parameter, so I can twist all of the values in that plot just sideways. Okay, so I'm going to create this new fake data, x and y. Our figure and our grid spec are just copied from above, and same with our top side and our lower right subplots for our histograms and scatter plot. Then in the lower right, I'm just going to call scatter, and I'm going to toss it all the data. For the top, I'm going to give it the x values and indicate that I want the bins to be 100. And for the side, I want the bins to be 100 and the y data. And I'm just going to set that orientation to horizontal so that it shows up sideways. So with this, it becomes immediately clear that we've actually got 2 different distributions. Now, we don't really care about the value of the y-axis for the top histogram or the value of the x-axis for the bottom histogram. Since these are probability density histograms, we only care about the relative values. And in Matplotlib, we can do this indicating that our histograms are density equals true. So this cares less about the actual frequency observations and more about the probability or the ratios of those frequencies. We can also invert the x-axis subplot for the histogram on that left-hand side, which makes it maybe a little bit more clear because it represents the data on the right-hand side. So this makes it look like it's sort of growing out of that scatter plot data. And we can use this directly using the invert x-axis function on the axes. Finally, we can see if we look back there that we've got a little bit of white space on the axis and a little bit of padding in there that's added automatically. And it seems unnecessary and maybe a little bit more confusing. So we can get rid of this by changing our axis limits. So you see here my approach to doing this is to iteratively build up the data, the investigation of the data, and a little bit of how I'm going to plot that data or look at that data. It really is this iterative process where I don't sit down and I know exactly what I want to see necessarily, but as I discover things or think about things or look at things, I can use Matplotlib to change how it's happening. And this works really well in the Jupyter notebooks. So the fake data is the same with the grid spec, same with our subplots, and same with all of our side histogram, top histogram, and lower right. But then I want to take that side histogram and I want to invert the x-axis, and then I just want to change the axis limits to get rid of the white space. So I'm going to iterate here for all of the axes in top histogram and lower right. I'm going to set the x limbs to 0 and 1, so I'm hard coding those. And here I'm going to set the y limbs to -5 to +5. And there we go. We can see that our top histogram is a random, pretty uniform, and that the histogram for the y values indeed looks like a normal distribution. In fact, this image sort of crudely looks like the image we looked at in the first module of this course from the MIT and Harvard study on MOOC engagement. And it should be pretty clear to you now how we might adjust various aspects of this plot so that if we wanted to make it look even more like that engagement image, we could. Actually, why don't you try it? Do you think you could add titles to these subplots and that are a little bit more similar to the ones from MIT and the Harvard publication? Or maybe change the individual point sizes because we're dealing with pretty big data. So instead of it being so big, why don't we make it nice and small? Or how about the styling? Could you change the colors of the plots to mimic the ones from MIT and Harvard? Give your newfound Matplotlib skills a try. Grab the API documentation and see what you can create. A box plot, sometimes called a box and whisker plot, is a method of showing aggregate statistics of various samples in a concise manner. The goal of the box plot is to summarize the distribution of your data through a visualization of what's called the 5-number summary. The extremes, often the minimum and maximum values, the center, usually the median of the data, and the first and third quartiles of your data. The quartiles of your data break it into roughly 4 different similar-sized buckets. And so the first and third quartile markers, these are sometimes called the hinges, show you that middle 50% of your data. Through the box plot, we can get a sense of the weighting of the data in a fairly concise, compact visual representation, and it's extremely common in data science. Let's take a look at box plots in Matplotlib. Okay, first we're going to bring in our libraries, pandas, Matplotlib, and NumPy. Now, I'm going to create 3 different samples from NumPy, one for a normal distribution, one for random, and one from the gamma distribution. So we can actually just look at these distributions and how they differ with respect to this 5-number summary. And I'm just going to stuff those into a data frame and name them normal, random, and gamma. And let's take a look at what this looks like. Okay, so we've got 10,000 points in each one of these. We can see all of our samples for normal in this one, random in the next, and then our gamma distribution in the far right. Now, Pandas has this handy function called describe that allows us to see this 5-number summary, some of those summary statistics that we're interested in. So let's call describe on that data frame and take a look. So we could see here that the mean actually varies quite a bit between these. The normal distribution mean is very close to 0. That's because when we don't parameterize it, that's exactly what it's calling from is a distribution function at 0. For random, it's very close to 0.5. Similarly, when we don't parameterize, it's going between 0 and 1 and picking random values at random. And so you'd expect with enough values, it would get close to 0.5. But we see the gamma is up around 2. We can also see the standard deviations, the minima, the maxima, and then we can see these hinge values, the 25% at the bottom, the first 50%, and then the 75% value. So this function, describe, shows those minimum and maximum values in the 3 different percentages. These percentage values make up what's called the interquartile range. There are 4 different quarters of data. The first is between the minimum and the first 25% of the data. And this is the value of 25%. This is called the first quartile. The second quartile is between the 25% mark and the 50% mark of the data. The third between 50 and 75, and you got it, the 75, and to the top is the fourth quartile of data. Like standard deviation, the interquartile range is a measure of the variability of the data. And it's common to plot this using a box plot. In a box plot, the mean or the median of the data is plotted as a straight line. 2 boxes are formed, one above, which represents the 50% to 75% data group, and one below, which represents the 25% to 50% data group. Then thin lines are drawn out to the minimum and the maximum values appropriately. Let's take a look. Of course, to see a box plot is really only a simple line. It takes me way longer to describe it than to actually see it. Here, we're just going to choose one column that we're interested in and pass it to the pyplots box plot function. Remember that Matplotlib uses NumPy arrays for data, but actually Pandas is built on top of NumPy, so things actually work fluidly. You can pass in a Pandas column because it is actually an ND array underneath. You'll see that Matplotlib actually prints out a bunch of information about artists. Often, we don't really want to see this, but it can be handy at times to get an idea of how that plot's being built underneath. But if we want to suppress this, we simply put a semicolon at the end of our last statement. Now, this is actually a Jupyter Notebook trick that I've used a few times here and haven't told you about yet. It suppresses printing the last variable in a cell. Be warned, though, it's not standard Python. Okay, so I'm doing the exact same thing, but this time I've added this sneaky little semicolon to the end. And that's going to display our box plot still, but it's going to suppress printing the object, which is all of the information about the artists. This gives us a basic box plot. Now, let's add the other two samples to it. Unfortunately, we can't just pass the whole pandas data frame to Matplotlib. Instead, we've got to pull out these columns and put them in as a list of values. It's not too much work, but it's a little more than I'd like. So to do that, I'm going to just make a new list for the box plot. So that's this syntax here. And then I'm going to put in our normal, our random, and our gamma. And I've got this other argument here, with, and I'm going to talk about that in a minute. But let's just take a look at what this looks like. OK, so we can see our three distributions. Now, we didn't normalize the scale, so that's a little wonky, I mean, to be honest. But if we look at the gamma distribution, for instance, we can see the tail of it's very, very long. So the maximum values are very far out. Let's take a look at this by itself in a histogram. So this is how I would, if I had some data and I saw the box plot summary like that, I might actually then decide, oh, well, I should actually get a better sense of what that distribution looks like. It wasn't quite what I was expecting. And so that's why I would plot it now in a histogram. Interesting. We see it starts at a moderate level, then spikes up, then drops off much more gradually, and does indeed have this very long tail. Let's add this to our box plot, and I'm going to take this as an opportunity to demonstrate something called an inset axis. Recall that we've got one figure, and inside of it, one subplot. Since we didn't do anything fancy with subplots, that means we only have one axis object. We can actually overlay an axis on top of another within a figure. And we could do this by calling the inset axis function on the figure itself and sending in the details of the new axis that we want to create. The details that we send in are the position in XY space of the original figure and the width and the height of this new axis plot. OK, so I'm going to create a new figure here. And in this main figure is actually the box plot that we just created. So I'm just going to call that box plot just again here. Now, let's plot on that axis a new axis object. And this wasn't something that you could do in Matplotlib a couple of versions ago. This was new in Matplotlib 3. Actually, you could use toolkits to do it. And I used to lecture on how to do that, but it's a lot more annoying. Right now, it's actually quite easy to do. So this is actually going to overlay on the top, and we're going to provide a bounding box of 0 to 0.6. This is going to be our bottom left corner. So 0 is the X position, and 0.6 is from the bottom of the figure to the top of the figure, how high as a ratio between 0 and 1. And then I'm going to use 0.6 and 0.4 as the width and the height, not the X and the Y of the right-hand corner or something, but it's the width and the height. Again, these are ratios of that underlying object. So I just call plot.gca, right? That's going to pull back our current axis, .inset axis, and then I just pass in all these parameters as a list. And that creates me a new inset axis object, AX2. So now with AX2, I can do whatever I want. In this case, I just want to plot that histogram of gamma. I'm going to set the bins to 100, density equals true. And since that histogram is right up against the left side there at 0, the tick labels are going to be kind of annoying, and they're going to clash with the main figure. So I'm just going to show you how you can flip them to the right. So I could take an axis, I can access the axis y-axis object and hit tick right. There's a lot of different words I'm using in there that all sound the same. Should be interesting to see how the transcript looks for this. OK, pretty cool, isn't it? So here in one figure, we have our box plots of 3 different distributions. And then we've got this nice little inset image showing the histogram of that far right box plot. Remember again that each box plot is our 5-number summary, a median line in red in the middle, and then the 2 boxes on either side of that, which represent 25% of the population respectively. And then these whiskers, which run out to the maximum and to the minimums of the data. This would be a great time to pause the video and play with the notebook to clean up this figure by adding titles, legends, and the like. How would you make it clear to the reader, for instance, that this inset histogram is about the box plot on the far right? Now, we often want to look at a box plot not by seeing the minimum and the maximum values, but instead by emphasizing the outliers. How outliers are detected really depends, and there's various mechanisms to determine whether an observation is an outlier or not. If we look at the documentation, though, the default for Matplotlib, which I actually showed right at the very beginning without telling you about it, is that outliers are all the data points, which are either greater than or less than the distance between the hinge, that's the bottom or the top of the box, or the first and third quartile, and 1.5 times the interquartile range, the IQR. The interquartile range is the distance between those 2 hinges, so that captures 50% of the data. So if we omit this WIS parameter that I've been adding to the box plot call, we'll see the outliers using this method. OK, so I'm just going to do that. I'm going to plot that box plot in a larger figure and show those outliers. So each circle in the box plot is a single outlier observation.
The box plot is one of these more common plots that you're going to use as a data scientist, and Matplotlib has significant support for different kinds of box plots. Here, the Matplotlib documentation is key, and you can find links in the course resources to the API, which describes how to use this box plot functionality. I've got one more plot to show you this week, a two-dimensional histogram, which is better known as a heat map. Then we're going to take a look at a couple more advanced features of Matplotlib.
Heat maps are a way to visualize 3 dimensions of data and to take advantage of spatial proximity of those dimensions. Now, in making revisions to this course, I was really tempted to get rid of the section on heat maps, as I've seen enough bad heat maps to last me a lifetime. The problem is heat maps are really quite powerful when you have the right data. Weather data is a great example. You have 2 dimensions, latitude and longitude, and then we can overlay on top of this a 3rd dimension, say temperature or rainfall amounts, and use color to indicate this through intensities of color. In fact, anything with 2-dimensional spatial aspects can be a natural for a heat map. As an example, eye fixation points through gaze detection is used regularly by researchers and marketing experts to understand what people are looking at on websites. But where heat maps break down is when there's no continuous, or at least no ordinal, relationship between dimensions. Using a heat map for categorical data, for instance, is just plain wrong. It misleads the viewer into looking for patterns and ordering through spatial proximity, and any such patterns would be purely spurious. But I decided to keep this into the course because it can be useful, and I put together a new example using ordered data. So let's talk about the techniques anyway. In Matplotlib, a heat map is simply a 2-dimensional histogram where the x and y values indicate potential points and the color plotted is the frequency of the observation. So let's bring in Matplotlib and NumPy as well as pandas and some datetime functionality. In this example, I want to show you some traffic data from New York City, which is all available from the New York City Open Data Portal. So I'm going to read that into a data frame, and then I'm going to convert out the date column into a date and time. So I'm going to take this pd.toDateTime, that's a function inside of pandas that'll convert that column for me and apply it across the date. And let's look at that data. Okay, that might take a little bit of time to load if you're following along on Coursera. It's actually quite a big data set. Now, let's take a look here. We've got these plaza identifiers. So these are the different areas where they've got the traffic cameras set up. And then we've got dates, and it's actually broken out by hour of the day. So for each plaza, each hour in the data set is broken out. And I think there's probably about probably 10 years of the data here. And then they have 2 different directions, incoming, which we see here as an I, and outgoing for the plazas, and then 2 different numbers. One is the counts of the easy pass, that's our density, we'll call it eventually, and then the VToll, that's a different tolling system. So these are 2 different tolling systems. All right, let's pare this down and do some basic exploratory data analysis with histograms. So let's say I'm interested in a single plaza, 1 camera location, and some of the dates for the early part of 2017. So I'm going to write a pandas query here to pull that data out. So I'm going to say df.query where the plaza ID is 5. I just picked that identifier, and the date is greater than the end of December in 2016, but it's less than the 5th month of 2017. Now, this syntax might look a little bit different to you from our first course. This is an alternative way to query a data frame, and it uses a library called numexpr to take a query in as a string and apply it to a data frame. It's a bit like SQL in its syntax, if you're familiar with that, but it has a lot of little caveats with it. I wanted to expose you to it so that you are aware, but it's completely possible for you to use the regular Boolean masking method I showed you in course 1. Actually, now would be a great time to pause the video, open the notebook, and see, can you rewrite this query based on what I said and what you see there, using the knowledge you already have on Boolean masking. We have the hour of day here, so let's take a look at a histogram of activity over day. So since we've got 24 hours in the day, I'm going to set the bins there, and I want to see our frequency. That's the weights for each bin as the number of vehicles just that have used this Easy Pass system. This system automatically bills drivers for using the road, and it's already been aggregated, that is summed up for us from the individual observations in the data set. So here to do this, we just say plot.hist. I'm going to indicate an array or a column in pandas because pandas is built on top of ND arrays of hour. So those will have numbers from 0 to 23. I want 24 bins in it because I know there's 24 hours in a day. And I'm going to set the weights as equal to this other column, the vehicles in the Easy Pass. I see 2 spikes, mornings around 7:30 and afternoons starting around 3 and going until 6 o'clock. So this is kind of rush hour traffic in New York. And this is what we might expect. In this example, our hours are ordered, starting at 0 and going till 23 throughout the day. So it makes sense to view the data in this way, as this continuous histogram. But we also have days of the week. Those are ordered as well, Monday through Sunday. So let's extract the day of the week and look at a histogram of that. So we can extract the day of the week from the date column using this pandas datetime feature .dt. So remember, a single column in pandas is a series object. It actually has this attribute .dt on it, which stores numerous datetime transformations for us because it's actually such a common need. In this case, we want to take this date column, we want to access these datetime functionalities, and we just want to get out of it the day of the week. I'm going to assign that into a new column just called day of the week. This will return to us a number between 0 and 6, depending on the day. And then once we have this, we can just tweak our histogram a little bit here, set our bins to 7, indicate we're interested in days of the week, and we'll still keep looking at the easy pass numbers. Okay, so we can see that the traffic flow is pretty steady, except for days 5 and 6 in the week, which happen to be the weekends. Now, we could isolate those days and look at the individual histograms for hourly traffic, but we could also look at a joint histogram, or a heat map, for both the hourly and the daily variables. When we do this, we set one variable to be the x-axis, another to be the y-axis, and then we render our frequency, our weights, using different colors, showing this third dimension. While it sounds like a lot of work, it really isn't in Matplotlib. The API looks almost the same as a regular histogram, but in this case, we have to specify the bin size for each axis. I'm going to make the figure a little bit bigger here so it's easier to read. And then we just call this hist2d instead of hist. We pass in our x and our y, so on the x-axis, I want to look at hours. On the y-axis, I want to look at days of the week. And then for bins, we have to tell them, well, there's 24 bins for the hours and 7 for the days of the week, and we leave our weights the same. Now this next part is actually optional, but it actually tells Matplotlib to show us a color bar, a legend, telling us what those weights mean. Okay, great. Let's dissect this a bit. First, we see that across all days, our y-axis, the first 4 or so hours of the day are dark blue. This is the first 4 columns or so, indicating that there's relatively little traffic. That makes sense, not a lot of people driving at that time. Then we see that for the days 0 through 4, we get these spikes in traffic, and those are shown as more yellow intensity cells in the image. But this isn't really true for those last 2 days, the weekend, the top 2 rows. Time data is an interesting use case for heat maps because we often have cycles of activities within a time period. In this case, we had days and we had weeks, and that allows us to have these 2 different ordered dimensions. Now would be a great time for you to grab control and see if you can look at a different dimension, months. Could you plot a heat map where one axis is months and the other is, say, weeks of the month? Give it a try. So far, we've focused on static images, but Matplotlib does have some support for animations. This requires a separate library to use in the Jupyter Notebook called IPyML, and I've installed that for you here. Animation depends on this library because it provides a new backend for us, the widget backend. So let's turn that on. So to turn on a new backend in Jupyter, we use the Matplotlib magic function, it's called. So this is actually just a function that's been written for us called Matplotlib, and we start with a % there, so it's a cell function. And we just say widget, and this tells us to initialize Matplotlib using the widget backend. You've got to do this at the very beginning of your notebook, or before you've used Matplotlib. You can't change it once you've set it, so be aware of that. I'm also going to bring in a number of other libraries we're going to need. So pyplot, numpy, but I'm also bringing in this matplotlib.animation as animation, and we're going to use that. The Matplotlib animation module contains important helpers for building animations. And for our discussion today, the most important object we're going to use is called func animation. This builds an animation by iteratively calling a function which you get to define. The function's job is to clear the axis object and redraw the next frame of the animation. Then these frames are all stacked together into a playable video. I like to use this demonstration in my class here at Michigan to show students how distributions can be sampled from. So we're going to build a basic animation, which is going to pull out 100 samples from the normal distribution. Let's generate that data now. Okay, so I'm going to set n equals to 100 here. That's the number of samples. And then I'm going to make x our just list of samples and we're just going to pull them out of the random normal distribution. Okay, next what we want to actually do is create that function that's going to do the plotting. I'm going to call this function update. You can call it whatever you want. Now, the Matplotlib func animation object is going to call this every few milliseconds and pass in the frame number we're starting with a frame of 0. So we can use this actually as an index into our array of values, which we've called x. The very first thing we want to do is see if the current frame is actually at the end of our list. If so, we're going to tell the animation to stop. And we do this by calling the stop object on the event source object attached to this func animation object. Let's take a look. So I'm going to create the function that's going to do the plotting. So it's called update, and it's going to pass in cur, where cur is the current frame. So it's going to be an integer value, starting with 0. The very first thing I'm going to do is check if the animation is actually at the last frame, and if so, I'm going to stop the animation. So if cur is equal to n, 100, then I'm going to call a.eventSource.stop. What's this a? Well, it's actually an object that we're going to define in a minute, and it will sit outside of this function, but we can still access it since Python allows us access to variables in the global scope. Okay, now on to the actual work. First thing we want to do is clear the current axes. We can do this by calling plot.cla, clear axes. Now, I just want to plot a histogram, but I'm going to set my bins to a predictable value so it doesn't jump around. So you can play with this. I'm going to use np arrange from -4 to 4, and I'm going to set these in half-sized steps. Then we're just going to make this hist call to pyplot using the current frame number, which was passed into the function. So here I'm just going to slice data out of x, whatever data we have up until the current. So the first time through, it's only going to be 1 item. The second time through, it'll be 2 items. The third time through, it'll be the first 3 items, and so forth. And I'm always going to set my bins to 100. So I'm always going to use full 100 bins so that doesn't jump around. And then I want to set my axes limits as well. All right, finally, I'm just going to add some nice labels here to make it look a little pretty. Okay, most of our hard work is done, but now we have to view it. To do this, we want to just generate a new figure and then call this func animation constructor. And we're going to assign this to variable a since we need to be able to stop it in that update function we just wrote. The first parameter is the figure that we're working on. This isn't really important, so we're just going to use the pyplot scripting interface to manage the figure. Then the name of our function and the amount of time we want between updates. And I'm going to set that to 100 milliseconds, which should be fast, but not too fast. So once we've got it all set up, it's actually quite quick to start. I'm going to say animation.funcAnimation, and I'm going to pass in a figure. So remember, plot.figure is just going to create a new figure. I could have used plot.gcf, get current figure, because that will also create us a new figure there if we wanted to. Or I could have created the figure, stored it in an object, and then passed in that object. Lots of options here. And pass in a reference to the function that we're using, in this case, update, the one we wrote. Maybe you changed the name, so you can change it here. And then our interval in milliseconds. And then all we do is tell the widget backend that it's time to start the show. And so we can see that we pull out these values from our x, and we're slowly building up what that distribution looks like. Now, if you run this on your system, you should see something different. It should be roughly the same as this, but it might be different. It's likely to be different because I didn't set a seed value, so we're all getting different random values. And this really demonstrates how, as you sample from a distribution, as the number gets bigger, it becomes more clear that it looks like that traditional bell curve shape. We see that there's some other functionality here that this backend gives us. We can save the image, we can pan around the image, and so forth. And those are useful in various different circumstances. Okay, there we go. A nice example of how sampling from a distribution can be used with an animation. Func animation, like most other classes in the animation package, is a subclass of the animation object. The animation object has a handy function which allows you to write the image to a file, a save function. This requires additional third-party libraries, though, like FFmpeg, and that can take a bit to install and set up. The result, though, is that you can fairly easily export your animations directly from the Jupyter web programming environment to M4Vs, MOVs, animated GIFs, and so forth. You know, a figure animation with 4 subplots, one for each kind of distribution we might be interested in understanding, could be actually pretty neat to see. I imagine we could plot the samples for a normal distribution in one, for let's say gamma distribution in another, maybe another couple of parameterized distributions, like a normal distribution with different levels of standard deviation. This would actually be a great way to practice the skills that you've learned in this module, as it would require that you manage multiple subplots with an animation using histograms. If you want to tackle that challenge, I'll put a link in the course shell to an optional practice notebook for you to take a look at.
This lecture is a bit different. It's an extended topic that looks at the interactivity functions which are available within Jupyter. Jupyter has this notion of widgets that allow you to build simple dashboards within notebooks to aid in your investigation. Now, you could read more about Jupyter widgets here, and please keep in mind that while everything I'm showing you should work fine in the Coursera system, it's quite likely that this fast-moving world is already a bit out of date with what I'm showing you. We're going to be using the interact function, which comes as a decorator in Python. So I tend to bring this in from IPyWidgets, so IPython widgets. Jupyter's built on top of interactive Python, IPython, so that's where the name comes from. So from IPyWidgets, I'm going to import interact. And then I'm actually going to bring in all of IPyWidgets as widgets, and I'll show you a couple of the different ones. A widget is just a little thing that's on the user experience, like a button or a drop-down or a scroll bar, if you're not familiar with the word. Now, I'm going to look at a small data set of real data that I collected of my own biking. So I'm going to bring in pandas and Matplotlib's pipeline. This data set's actually pretty important to me because while I was biking in 2019, I went into a roundabout, it's a traffic circle, a little too fast and I just completely biffed it. And so this makes it actually a great thing to visualize. So let's read that into a data frame. I know that there's a timestamp in there, so I'm going to set that as the index and let's take a look at what that data looks like. Okay, so here's what that data looks like. The data set's made up of time and a set of the sensors that I was wearing while I was riding. These sensors picked up details such as my position, my elevation, my speed, my heart rate, and more. I assume now everybody's kind of going for bike rides like this, and it's really quite nice to be able to reflect on your ride, not just the things you saw or the physical exercise, but of course in the data. So Pandas has some built-in support for plotting, but it needs to be able to talk Matplotlib. We do this by indicating that we want our Pandas plots to convert automatically for us. So from Pandas plotting, I'm going to import register Matplotlib converters and then just run that function. And that'll allow Pandas to convert data types back and forth. Not all of the columns in my data frame are actually all that good to visualize in a line plot, and that's what I want to show you here. So I'm going to iterate through my data frame and just keep a list of the columns which are not of type object. That is, the column is a number. Now, I don't have to do this. I could have just picked the columns that I wanted to use, but I'll be honest, I actually write this quite a bit when I just load in a big wide data set and I want to look at one of these sploms or I want to look at some relationship. Sometimes I just want to get out everything that I could plot against one another and look at those. And so this is sort of a little bit of a recipe I use. It's just iterating across all the columns and pulling out everything that is not an object, which means I've got to do some string processing or the like with it. Okay, now I want to write a plot wrapper function. This function is actually going to plot one or two columns, but never more. If there's a single column passed in, it's just going to plot that in the default blue color. But if there are two, it's going to plot the one column of data on top of the other, with the second column being in red. And I'm going to use the plot.twinx function here to ensure the x-axis is the same. It's going to be time, in this case, the data frame index, but that the y-axis can be unique for each series of data. So all I do is call plot.figure with the figure size I want. I get the current figure. I set the title. I'm just going to set it to the column names. And then if there's two columns set in, I'm going to plot, twin the axis, and then plot with a different color. Otherwise, I'm just going to plot in the default. Now, let's just look at one example of the two columns of data. And in this case, I'll just choose cadence versus speed. Okay, it's pretty messy, but we can see that there's a moment, maybe down around 2105, where the cadence and the speed did drop together. Anyway, let's go into the interactive part. To make this interactive, we can wrap this function with the interact decorator. A decorator in Python is just a function which wraps another function, and the IPython team has written this one for us. It allows us to provide a new widget, in this case a select multiple widget, and use whatever is selected there as a parameter that's going to be sent to plot data. We can set this up by putting the decorator in front of the plot data function definition. So I'm going to do a little copy and paste here. The select multiple widget actually has three parameters. The set of options that are legal, so in this case it's going to be our potential column names. This is what will be shown to the user for their affordance, it's called. The values that we want passed in, so time's always going to be our first value that we want passed in, our x-axis, followed by whatever other values are selected, and then some descriptive string. So here I've got the interact decorator. So the decorator in Python, we just use the @ sign and then the name of the function that's actually written as a decorator. I say the column names, so that's actually mirroring what's in our function that we've written, the plot data function called call names. So we have to set that. And then I just assign that to the widget. And that means that the widget values are actually going to be passed in as the column names. For the widgets, I'm going to use the select multiple. So that's actually a drop-down list that allows you to select multiple items. I'm going to say that the options it should show are potential columns. This is that list of columns that we built up, everything but the object. And that the value is going to be the potential column sub 0. So that's our time. And then followed by any number of other items that are selected. And then the English word that I just want to describe this at is columns. Our plot data function doesn't change. So this I just copy and pasted before. You have to put the decorator right in front of your function, so we have to put this definition in there. Otherwise, it's just copied from before. And a reminder that what it really does is it looks, if there's 2 column names, then it's going to plot a blue and a red. Otherwise, it's just going to plot what there is. Let's run this. Okay, so you can see what Jupyter's done here for us. It's actually put that widget in front of our chart, and then it called that chart with cadence in it. So here is that select multiple widget, and it's given us all of the things that are potentially in our column. And so we can choose one, like distance, and we'll see that that chart just updates, right? So this is actually really nice. You can kind of look at a nice big visual of some of the things that you might be interested in. So then you could select something like speed and cadence here, 2 items, and you can see the 2 items being plotted against one another here, which is really quite interesting, right? It gives you the ability to, just make up a little hypothesis of what you're seeing at any time and then plot it. Now, sploms allow us to do this with small multiples, so you shouldn't discount that technique. But sometimes a dashboard can engage your reader in a different way and let them see a slightly larger view of that data. Let's look at one more example. Here I'm going to use a widget called an int range slider, which allows the reader to set a lower and upper bounds for something. I've written a lot here, and you could check the docs for more, but in this case, I'm going to look at a plot of my heart rate where the reader gets to see all the places between 80 and 100, but they can actually change this to filter based on values that they're interested in. I'm also going to create a text widget, so I'm going to use that one as well, that allows them to set the start and end time so that you can zoom in on a time of interest. So again, the interact has to be called that decorator right before the function. In this case, I call it plot heart rate. You'll see that plot heart rate has a heart rate bounds parameter, a start and an end. And if we go back to the interact, we'll see that there's a heart rate bounds. That's set to some widget. We'll see that there's a start. That's set to a different kind of widget, the text widget, and an end that's set to a third text widget. So we're going to have 3 widgets, and the values of those widgets that the user chooses are going to be passed in as parameters, and that plot function will be called dynamically. The int range slider has a minimum and a maximum value, or default values. 80 to 100 is what I've chosen, as well as that min max and a step count and a description. You can look at all of the details of this inside of the documentation. For the plot heart rate, all I'm going to do is take the heart rate bounds, the start and the end. I'm going to create a new figure. I'm going to set the X lim and the Y lim values as appropriate with respect to the heart rate. So you can see the X lim is going to be set to that left and right, and the Y lim is going to be the max of the heart rate. And then I'm going to filter my data frame and plot that scatter plot. So my actual plotting function is quite small. Okay, so here we can see the effect. I've got my heart rate, and you can see it's got this nice slider, and the min and the max has been set, and my 80 to 100 has been set, and it's telling me that here. And I've got the start time and the end time as was set in my data frame. And you can see that there's a whole bunch of points here between 80 and 100, and then they sort of disappear here. Now, because, it's cycling data, and it's likely that my heart rate increased, I can actually drag this out, let go, and then we'll start to see more data appear. So I'm allowed to filter based on that. You can see that I could also change the data here. So for instance, it looks like if I wanted to jump maybe 20 minutes more into my workout, I could do this, and then we can see the data's actually been pruned. It's not going to show me the data from before that time. Now you can imagine that we could do all sorts of things with these widgets. We could draw reference lines, we could change reference lines. You can actually have somebody select on the plot itself regions of interest as well. Okay, so that was a pretty whirlwind demo of Jupyter Widgets. The ecosystem for widgets is far from finished, but the functionality is being added all the time. I wanted to include this here because it's starting to get a bit more mature, and honestly, it's visuals like plots and charts that people want these widgets for. I hope you'll take a look and poke around with what's available, and maybe share your findings and creations with myself and the other students in the class.
Hi everyone, welcome to today's tutorial, where we'll be looking at visualization in Pandas. Pandas uses Matplotlib under the hood and provides some convenient functions for visualizing data. Before we dive into visualization in Pandas, let's take a look at the Matplotlib style package. Matplotlib comes with a number of predefined styles which we can choose from to change the default look of our plots. Because Pandas is using Matplotlib under the hood, this will change the default style of our Pandas graphs as well. We can use plt.style.available to see the predefined styles provided. Let's use the seaborn colorblind style, which will change the default colors of our plots to use a color palette that is more color vision deficiency friendly. Now, where the built-in visualization in Pandas really shines is in helping with fast and easy plotting of series and data frames that can help us explore the data. Let's make a data frame. First, we'll set the seed for the random number generator, which will allow us to reproduce the data. Next, let's add 3 columns of random time series data. We can generate the random data by cumulatively summing up random numbers. NumPy has a great function for this called cumSum, which cumulatively sums an array. Let's do this for 3 columns, A, B, and C, and also offset the B column by +20 and the C column by -20. Using date range, we can set the index to be every day in 2017. Now let's see what this data looks like a little more visually. To plot this data, we can use the plot method on the data frame. The plot method on series and data frame is just a simple wrapper around plt.plot. So when we call df.plot, we get a line graph of all the columns in the data frame with labels. Notice how the colors are slightly different from the default Matplotlib colors because of the style we used. Also, notice this cool Jupyter Notebook trick. If you add a semicolon to the end of the plotting call, this will suppress unwanted output, and this works with regular Matplotlib too. Dataframe.plot allows us to plot a number of different kinds of plots. We can select which plot we want to use by passing it into the kind parameter. Let's try and create a scatter plot that takes the A and B columns of df. We pass in scatter to the kind parameter to change the plot type. This is what we'd get if we called plt.plot on the A and B columns with the point marker parameter. Passing scatter into the kind keyword argument changed the plot type to a scatter plot. You can also choose the plot kind by using the methods dataframe.plot.kind instead of providing the kind keyword argument. Now let's try this and create something a little more complex. This time, we want to make a scatter plot with points varying in color and size. We'll use df.plot.scatter, pass in columns A and C, and set the color C and size S to change based on the value of column B. Finally, we can choose the color palette used by passing a string into the parameter color map. Here I'll use Viridis, which is particularly pleasing to the eye. Here we can see the A and C columns plotted against one another, with the size and color changing based on the values of the B column. Because df.plot.scatter returns a Matplotlib axes subplot, we can perform modification on this object just like objects returned by Matplotlib plots. For example, let's see what it looks like when we change the aspect ratio of the axes subplot to equal. Setting the aspect ratio to equal allows the viewer to easily see that the range of series A is much smaller than series C. Using Pandas, we can also easily do box plots, histograms, and kernel density estimate plots, which are useful for visualizing an estimate of a variable's probability density function. Kernel density estimation plots come in handy in data science applications where you want to derive a smooth continuous function from a given sample. Pandas also has plotting tools that help with visualizing large amounts of data or high-dimensional data. Let's explore a couple of these tools by loading in the iris flower dataset. The iris dataset is a classic multivariate dataset which includes the sepal length, sepal width, petal length, and petal width for hundreds of samples of 3 species of the iris flower. Pandas has a plotting tool that allows us to create a scatter matrix from a data frame. A scatter matrix is a way of comparing each column in a data frame to every other column in a pairwise fashion. Let's use it to visualize the iris data frame and see what insights we can gain from our data. The scatter matrix creates scatter plots between the different variables and histograms along the diagonals. This allows us to quickly see some of the more obvious patterns in the dataset. Looking at the scatter plots, it appears that there are some distinct groupings of the points, which might indicate that there could be some clustering going on. And while this looks impressive and is certainly useful, realize that in the last 2 weeks, you have gained all of the skills to manually build these kinds of plots if you want to. This is nothing more than a 4x4 grid of subplots, with some plots histograms and the others scatter plots. Let's look at one more plotting tool in Pandas, which will help us visualize multivariate data. Pandas includes a plotting tool for creating parallel coordinates plots. Parallel coordinates plots are a common way of visualizing high-dimensional multivariate data. Each variable in the dataset corresponds to an equally spaced parallel vertical line. The values of each variable are then connected by lines between for each individual observation. Coloring the lines by class, in this example the species of flower, allows the viewer to more easily see any patterns or clustering. For instance, looking at our iris dataset, we can see that the petal length and petal width are 2 variables that split the different species fairly clearly, with Iris virginica having the longest and widest petals, and Iris setosa having the shortest and narrowest petals. Well, that's it for visualization in Pandas. In the next video, we'll look at Seaborn, a powerful package for statistical plotting. Hi everyone. Today we'll be looking at Seaborn, a Python visualization library based on Matplotlib. Seaborn is really just a wrapper around Matplotlib. It adds styles to make default data visualizations much more visually appealing and makes creation of specific types of complicated plots much simpler. To get us started, I've imported Seaborn as SNS. Now, let's set the seed for the random number generator, which lets us reproduce the data. Next, let's make a pandas series V1 that's 1,000 numbers drawn from a normal distribution with a mean of 0 and a standard deviation of 10. Let's also make a second pandas series V2, which is 2 times V1 plus 1,000 numbers drawn from a normal distribution with a mean of 60 and standard deviation of 15. Now let's see what the histograms of these 2 variables look like when we plot them side by side. We can set alpha equal to 0.7 so the histograms don't cover one another up. For the bin parameter, instead of an integer denoting the number of bins we want, we can also pass in a specific sequence using np.arange to specify the specific bins we want to use. This is useful for when we want to plot 2 histograms in the same figure to make sure the bin sizes are equivalent for both histograms. We also add labels so we can see which histogram belongs to which variable using a legend. Looking at the histograms, we can quickly see that V1 has a lower mean than V2, and that V2 has a larger spread than V1. Even though up to this point we've only used Matplotlib for plotting, we see that even just importing Seaborn has changed the aesthetics of the plot to a different style from the Matplotlib default. Let's visualize these histograms again, but in a different way. First, let's pass in both of the series V1 and V2 in a list and set the hist type to bar stacked. Setting normed to true will normalize the histogram to form a probability density. Next, let's create a variable V3, which is the combination of V1 and V2. We'll use V3 to plot a kernel density estimate plot over the stacked histogram. The kernel density estimation plot estimates the probability density function of the variable V3. Plotting it on top of the stacked histograms of V1 and V2 allows us to see the relationship between these 2 visualizations. Seaborn provides a convenient function for these type of plots, sns.distplot. Let's take a look at how it works. We can pass in the variable we want to visualize, along with keyword arguments for each of the individual components of the plot. Let's set the histogram color to teal and the KDE color to navy. Now let's look at an example of one of the types of complex plots that Seaborn provides a convenient interface for, the joint plot. The joint plot creates a scatter plot along the histograms for each individual variable on each axis. You've actually seen joint plots in Module 2 and created them manually yourself. To create a joint plot, we just type sns.jointplot and pass in the two series, v1 and v2. Setting alpha to 0.4 will help with visualizing overlapping points. The joint plot allows us to visualize the distribution of the two variables individually, as well as relationships between the variables. Using joint plot, we can see that v1 and v2 appear to be normally distributed variables that are positively correlated. Because Seaborn uses Matplotlib, we can tweak the plots using Matplotlib tools. Some of the plotting functions in Seaborn return a Matplotlib axes object, while others operate on an entire figure and produce plots with several panels, returning a Seaborn grid object. In both cases, Matplotlib can be used to further tweak the plots. For example, sns.jointplot returns a Seaborn grid object. From this, we can pull out a Matplotlib axes subplot object using grid.axjoint. Then we can set the aspect ratio to be equal using setAspectEqual. Hexbin plots are the bivariate counterpart to histograms. Hexbin plots show the number of observations that fall within hexagonal bins. sns.jointplot includes a hexbin style we can use by passing in hex to the kind parameter. The hexbin style of plot works well with relatively large datasets. Another good option for visualizing the distribution of datasets is kernel density estimations, or KDE plots. You can think of two-dimensional KDE plots as the continuous version of the hexbin joint plot. First, let's tell Seaborn to use a different style using sns.setStyleWhite. All of the following charts will have the gray grid turned off. Now we'll create a joint plot just like before, except this time, let's set the kind to KDE. Finally, let's set space to 0, which will plot the marginal distributions directly on the border of the scatter plot. We can see that Seaborn has some built-in options for easy customization and provides us with easy-to-create and beautiful plots for exploring the distributions of your data. For the last part of this tutorial, let's load in the iris dataset to see how Seaborn handles visualizations of categorical data. Similar to pandas, Seaborn has a built-in function that creates a scatterplot matrix. We pass in the iris data frame, tell it to map name to different colors using the hue parameter, and tell it to use a KDE along the diagonals instead of the default histograms. Looking at the pair plot, it's clear there are some clusters in the dataset. It looks like petal length and petal width are good options for separating the observations, whereas sepal width is not a strong separator. Using pair plot to look at your data frame can be a very useful tool in exploratory data analysis. One final plot I'd like to show you is called a violin plot. You can think of a violin plot as a more informative version of a box plot. To demonstrate, let's plot a violin plot next to a swarm plot, which you can think of as a scatter plot for categorical data. First, let's create a new figure and a subplot. Next, we'll create the swarm plot, passing in name and petal length, and the data, which is the iris data frame. For the next subplot, we'll create the violin plot, again passing in name, petal length, and the iris data frame. Looking at the swarm plot, each species has its own column, and each observation's petal length is shown, with more common values appearing as the wider parts of the cluster, much like a histogram. The violin plot is like a box plot with a rotated kernel density estimation on each side. Violin plots convey more information than box plots and are able to show particular phenomena within the distribution that box plots are unable to convey, such as multimodality. Seaborn is a library that not only adds new styles and visual aspects, but also introduces new functionality, such as joint plots, scatter matrix plots, and violin plots. Seaborn is being actively developed and is easy to install, which makes it an indispensable part of a data scientist's toolkit. But keep in mind, this is functionality built on top of Matplotlib, and these are largely Matplotlib artists being used. So if you have any ideas for a new statistical visualization, or you read about one in a publication or journal, You should have the ability to create your own visualization toolkits. That's it for Seaborn tutorial. Thanks for watching. Happy plotting.
Capturing physical landscape traits in a written form is perhaps one of the oldest and most common examples of information visualization that's still in use today. Geographical Information Systems, GIS, are highly specialized and complex, made up of a myriad of unique techniques and tools. In this lecture, I want to just dip our toes into this world and show you how you can leverage GIS to lead to insight in computational narratives. We're going to start by bringing in a few of our common libraries, Pandas, NumPy, and Matplotlib's PyPlot interface. And we'll set some Matplotlib defaults. By setting these defaults in the RC params list, we can be certain that our figure size will be the same throughout our investigation. When you do this, make sure to do it at the top of your notebook before you actually start using Matplotlib. So I'm going to import Matplotlib, the module, as MPL, and then I'm going to set the figure size to be 16 by 8. That's in inches on my system. Okay, now I'm going to bring in some data on cycling. So this is actually an interesting data set called wipeout.csv. I'm going to read that in with pandas, and let's take a look at this. Okay, so this data is made up of latitude and longitude, a timestamp on what looks to be about second frequency, as well as measurements such as heart rate in beats per minute and enhanced altitude, probably in feet, speed, all sorts of things in here. The first thing we need to consider when mapping is longitude and latitude. Now, cartographers for thousands of years have come up with different ways to take a mostly round globe and turn it into a two-dimensional rectangle, and these methods are called projections. If you're going to work a lot with cartography data, then you're undoubtedly going to have to learn some of these projections. I'm not an expert at all in these different kinds of projections and the way mapping coordinates are stored, but even in this simple example, it looks odd to me. Why do we just have a single number? I'm used to seeing some periods in there or decimal places from when I use Google Maps. It turns out that this particular data source is trying to capture the maximum precision possible in an unsigned integer. So we first need to convert these to a more traditional decimal format. To do this, you're going to have to go to the docs and identify how to do the transformation, but I'm saving you that step here because I actually already know what it is. Okay, if we multiply by 180 degrees, then divide by 2 to the power of 31, we get to convert our units into something a bit more meaningful, the kind of thing that you would see as GPS coordinates. But it turns out that that doesn't really do everything we need. You see, the Earth is kind of round. It's not quite round, but it's pretty round. And we're going to try and look at it on a screen, and the screen is pretty flat. Actually, my screen in front of me is quite curved, but we're still going to look at it in this two-dimensional projection. Because we're going to plot on top of a two-dimensional image, we're going to want to use the Mercator projection. I'm going to share with you the code to convert from latitude in degrees to a flat Mercator projection. And this actually comes from the OpenStreetMap effort, and I've got the URL here. And so I just wrote this function, lat to y, here, and I'm going to apply that function to the latitude degrees, and I'm going to store it in a new one called position lat degrees Mercator. Lastly, I want to drop anything with missing values. Now, this is a simplification for the moment and might not be actually what you would want to do in practice, but I'm going to just try and reduce it down a little bit. The first approach to plotting I want to show you is probably the most simple. The gist is that we're going to render an image behind an axis object, and then we're just going to use our regular plotting on top of the axis object. For this to work, it means we need an image, and we need to know the coordinates of the image bounds. Then we can set what's called the extent, which represents the bounds of the map. This means that our image behind the axis object will use the same coordinate system as the axis object itself, and the plot will be locked. So first, the image. I got mine through an export from OpenStreetMap, and I just saved it here in Coursera as map.png. And you can get a map directly from OpenStreetMap. To display this, we're going to use the pyplot imRead, image read function, and pair it with imShow, image show. So we just do plot.imRead, and that reads it in, a nice binary object here. And then when we call plot.imShow, we can pass in the image, and then we can set that extent, what the bounds are in that image, as reference for our data set later. Okay, great. That created a map, and we can see that the x and the y-axis are constrained by the extent that I set up. Now, the extent doesn't really matter. You can choose whatever you want. Just make sure it aligns with whatever your map is. In this case, I know what it is from my map, what I exported from OpenStreetMap. And so you can see that the axis labels for the x and the y-axis are actually being added because of the extent I set automatically by Matplotlib. Now, it's actually really easy to overlay our data on top of this plot. We just use whatever plotting functions exist in PyPlot that we're interested in using. In this case, I'm going to use the scatter function, and I'm also going to add a color bar as well and change the values of the dots being plotted based on the heart rate column in our data. Okay, so first I'm going to re-show the image. Remember, after each cell in Jupyter, by default, it closes the image. We could actually change that inside of Jupyter. We can set some RC params for that, but I'm just going to replot the image. Now I want to take our longitude and Mercator projected latitude data. We can set the series of data we want to be the colors of points using the C parameters, and we can choose from different color maps using the CMap parameter. Also, I'm only going to plot those points which actually appear on the map itself. So this is a little long here, but here I'm taking our data frame and I'm just going to look and slice it up by position longitude between these values and position latitude degrees Mercator between these values. And they kind of match my extent values up here. And then I just call scatter, just like we did previously. I indicate my X and my Y. I indicate how big I want the points to be, what I want the color to be derived from. And so in this case, it's the heart rate value, and what color mapping I want to use. In this case, I'm going to use blues. Then to add a color bar, we can just say plot.colorbar.setLabel, and we can give it a little bit of a useful label, and then we can indicate the title for our plot as well. Nice, we've got a map, and we have some points plotted on the map showing the various heart rate measurements. If you look at this, you'll notice that the lighter, more transparent circles are closer to 100 beats per minute, while the dark, full circles are close to 135 beats per minute. With a bit of insider knowledge, since it was me on the bike, I can tell you that the street in the lower left corner here is actually a hill that I would cycle up, and that this part here is actually a hill that I'm cycling down or coasting down, and so my heart has not got as much work to do here. Now, this method of creating a map using an image with extents is simple and reliable, but it's not really fast or seamless. If we just tossed our full data frame on there, it'd become apparent that we need to go find a map with the right extents to do the plotting, and we're constantly looking up different maps that we want to export to make in as part of this background image. So let's see that exact same code, but with all of the data. So that's actually easier for us to do because I first just show the image and then I just scatter plot everything. I don't have to have that big Boolean mask. So now we get to see my whole cycling route, but we only have this tiny portion of the map right down here. An alternative approach taken for maps in most web systems is to use what's called a tile server. Tile servers actually create a matrix of maps at different zoom levels, and then they serve up portions of the map, the tiles, as requested from the client. This is how Google Maps, for instance, works, and it creates a responsive experience at the cost of being a bit more fragile as the network access is needed. This paradigm is actually also available in the Jupyter notebooks as well through a project called Folium. This project is all client-side JavaScript and does the map requesting and rendering. To connect this to our Python backend, we can use the Folium project. Be warned though, this is a new library. It takes us out of the Matplotlib world, but I think you might find it pretty usable, pretty natural, and something that you might want to use if you're actually going to start looking at maps and doing plots on top of maps. So I'm going to import the Folium package. Now we want to render a spot from our previous data. So for this, I just picked the center point of the map and then we set a zoom level. There's different zoom levels you can choose here and you'll be able to scroll up and down in them here. And a key eye is going to notice that I had to reverse our longitude and latitude for this library, and I'm not using the Mercator changed values for longitude. So welcome to GIS systems, where each system is done just a little bit differently. After I create that map, I'm just going to display it here. Okay, so you'll notice immediately that the user experience is nice. You can still see the data once we plot it, but you can actually zoom in and out. You can move around the map just like you could in Google Maps. And when you move off and see tiles that aren't there, they actually get picked up automatically by the system. I'm going to bring that map back here. So we can add callouts to the map using the marker class. Let's set this for our start and end. So here I'm going to create our map again, and then I'm going to create some markers. The first one here I'll call start. I just set the pop-up as the start, and I'm going to take the iLock 0. So that's the very first item inside of our data frame, inside of that column, for both the latitude and the longitude. And then I'm going to do the exact opposite, or rather the same thing, but with a -1. So I'm taking the last item for the latitude and the longitude for the stop. These are going to put these little pins up that indicate what the start and the stop of the route was. But I also want to map the whole cycling route. The docs for Folium point to a polyline as the appropriate class to use. The polyline takes a list of locations as tuples, which means we have to combine our latitude and longitude values pairwise. And this is actually easily achieved through the use of Python's zip function. So when I take zip here, I give it two different columns, it's going to item by item marry those things together and turn it into a sequence, or an iterable at least, of tuples that have the two values in there. And so that's what the polyline's looking for, is the locations as XY positions, or rather it's as latitude, longitude positions. And then I'm setting the weight to be 5 and the color to be blue, and then I'm adding it to the map. And let's just render this. Okay, well, that's a nice rendering. So you can see here my cycling route. You can zoom out of my cycling route. You can see the little pins here, start and stop, and you can see where I went off to. It's really quite a nice and a very fluid approach when you want to start looking at data. And each one of these, even though we're using a polyline, each one of these is actually all of those data points are directly plotted on there and then joined automatically for us as part of that polyline. The docs really demonstrate how to use Leaflet, which is part of this Folium world, to do interesting things, and they've been well optimized for the browser and the JavaScript world, including setting colors through HTML color codes and events so that you can capture interactivity. This is just the tip of the iceberg when it comes to using Folium and Leaflet, and I would encourage you to dive into those docs and play around with them a bit more to learn. In this lecture, I've just touched on some of the information mapping that you can do, mixing GIS structures and data. We've seen several different approaches, from rendering a simple data plot superimposed on a map to drawing on top of a JavaScript-based map with Folium. GIS systems are a huge area, but it's helpful to know a few things about spatial representations of data for those times when the physical is part of your investigation.